Ben.
Is it my dodgy PowerPoint?
No, I don't think so. We've had it on for days.
Just have a really stroby presentation.
Just,
That's it, yeah.
yeah, there we go.
Tell you what, instead of standing here like a plum, I'll just tell you what up mixers are generally used for. So essentially, a lot of, is that too distracting for me to talk over the top of? It is a bit, and I can see it reflected on all your faces.
Sorry.
Is it okay if you come out of full screen, perchance, and then we can just roll it off the off the desktop? Yeah, it could be. It didn't seem to flicker as much. Yeah.
I think it's going into another screen mode.
Yeah, it's doing very well.
We've got a different screen.
Display port extra one.
Yeah.
Display port extra one.
Alright, cool.
Give us a song.
Not good with songs.
It's like we become engineers, isn't it?
Alright, try that.
I've got a different machine, if that's worth a try.
What's it going to? This?
Are we all comfortable with short time Fourier transforms? Genuine question. If not, it's okay.
Comfortable mathematically, comfortable acoustically.
Just the idea, the concept, just the concept.
Should I put my speaker back up?
I think that might have done it, yeah.
Yeah. That's too much white.
There's a
He doesn't like your white.
there's a PDF copy, or is it just the white's an issue?
Stay on the desktop.
Try 1080.
Just make it bigger. Don't want interlace. No, please.
Just full screen the. Oh.
No.
Just try full screen the PowerPoint, whatever it's called, thingy. Are we on a live stream?
Yeah, we are. Yeah.
Is that camera one? You camera one. You camera one. Don't know. All right.
Did we put out an epilepsy warning before the...
It's all right. They're running at an extremely slow frame rate. It's just static. There we go. I'm happy with that if you're happy with that. Cool. All right. I wonder if this thing, dare I? Woohoo! All right, you happy?
We'll do that for now.
Bruce, thank you so much.
Troubleshoot that at dinner time.
Really appreciate your help there. Thank you so much. Okay, so program material, commercial music, all the rest of it. It's mostly 2-channel stereo. And the idea behind upmixing is that we want to increase the listening area. So for stereo, the general setup is you have a left speaker, right speaker, central listening position. As soon as you move towards one of the speakers, the image tends to collapse. So we heard a bit about that in the last presentation. So what we can do is put a center speaker in, for example, but then comes the challenge of actually extracting the information for said channel. So what needs to go to drive that center speaker? So that is the challenge of upmixing. You take 2 signals and you massage it into more. Now I'm going to be talking about 2 channels to 3 channels. So instead of having left and right, we're going to have left, center, and right. And I'm not going to talk about any of the ambience extraction for surround, etc. We're going to keep the problem really, really succinct. Okay? Now, some approaches. Oh, going backwards. Some select approaches. We got mid-side, which was mostly developed, well, it's been around for a while, but it was pioneered by Michael Gerson, bit of a legend. Then you have the optimization approaches, principal component analysis, least means squared, adaptive filtering, and the two that are the focus of this presentation, which is sort of dynamic panning and calculation of gain parameters, etc., and an approach developed by Earl Vickers in 2009, which utilizes frequency domain extraction to actually define what a center channel signal should be from the left and right. Okay, so before we move on, why do we need to use, I mean, there's a whole plethora of different approaches to this. The problem is that each one comes with its pros and cons, as we can all appreciate. Mid-side sounds great timbrally, but the resulting image is actually quite narrow. So what you get in terms of an upmix, a sort of more stable, wider listening field, if you like, you lose extreme panned components. So instead of having your left-right, you end up with a left-center-right, okay? And you can read that basically just straight off the basic equations that are used. If you end up having a signal that is going to the mid-channel, i.e. left plus right, you add, say you've got a hard pan source to your left, and you add that into your center channel, you're going to pull the image into that second active arc, okay? And that's the most extreme pan you can have. So, bad idea. Or not a bad idea, it's just a different approach, but it doesn't have the extreme panning. That stays the same for all of these approaches that I'm looking at. They're not necessarily bad, they just have disadvantages. This one is the least mean square approach. So basically, the signal model is ever so slightly flawed in a way. It takes a lot of massaging to get right, and a few approximations need to be thrown in above and beyond what's actually published in the literature currently, as far as I understand it. So the main problem here is that we're looking to have a direct sound component, S, which there's only one of them. And this direct sound component exists in a particular time frame at a particular frequency band, okay? So that's where the short time Fourier transform comes in. We're looking at a frame of time, and then we're going to splice up that frame into different frequency bands, and then we assume that only one primary sound exists in that single time frequency tile. Is that making sense? So that is one of the underlying assumptions of most of these upmix approaches. But here there's a problem. If we have this direct sound in its time frequency frame, and it appears on the left-hand side, and nothing on the right-hand side, then S has to be 0 in order to not be on the right-hand side, and A has to be infinity. Bit of an issue. So this one actually falls flat on its face in that instance. And as I say, there's a few things that you have to mess around with in order to get it work. So we're not going to spend any more time on that one. Adaptive filtering is another approach, and this is one that's actually born more from control theory. And essentially what happens is you seek to extract a particular signal, be it a center signal, an ambient signal, an error signal, by constantly filtering as you go through a track. The problem with this is you can end up getting stuck in particular, well, high levels of volume, and you get this really sort of pulsing, almost like a compressor. It kind of ends up giving you this non-linear sort of effect, and it can be quite disturbing. So again, more investigation required on this front, but for now, let's move on. Now, this is my favorite, Kraft and Zolzy. Absolutely brilliant bit of work. So this came about in 2015 as a frequency domain approach. And consequently, in 2016, it was put into the time domain as well. So these are both DAFX papers from the respective conferences. And essentially, we start off with a sort of similar signal model. So our left signal is comprised of some primary component in a time frequency slice multiplied by some gain. And then we have an ambient component on the left side as well. The right side, similar. Now, the whole idea is that from this premise, you can essentially make a bunch of assumptions and then knock out some terms in these two equations and then solve for direct and ambient. All right? And once you have those, so essentially here we're saying, okay, let's just ignore the ambience. That's the first assumption. Get rid of the ambience, we don't care about it. Because the primary components are going to have more power. Fine. So if you do that, you wind up with your a different set of equations, and you've got 3 equations there, 2 unknowns, your 2 gain quantities. Okay. Once you've got your gains, you're home, you're done. So basically you can, from the law of sines, you can calculate the angle that that particular direct sound source in its particular time frequency slice is coming from. So where should it be positioned across the front arc, or indeed the 2 arcs that you now have, because you've got left center, center right, okay? And with a little bit of more assumptions, you can generally say that the ambience is kind of what's, it's the residual, it's what's left over in the left and right channel once you've extracted your direct sound. And you can apply a filter to one side to decorrelate it from the other, okay? And those are your left-right channels. All right. Vickers, really interesting approach, because this one says, right, okay, we're going to directly dive in and just extract what should be in the center. So the signal model here says that there's only one primary sound, again in time frequency, but it only ever exists on one side of center or the other. Okay? So if I have my primary component on my left-hand side, the gain is going to have a positive value, and the right-hand side is going to be 0. So that's given by the last equation. And in the time frequency domain, we assume that the ambience, or indeed the left and right channels, are decorrelated, so their correlation is 0. Proceed from there, and we can get our center channel and its respective gain. Okay? So that was that's a whole AES paper in one slide, all right? So I'm sorry if that wasn't enough of an in-depth explanation. All right. How am I doing for time? Am I going to have to rush?
You've got 12 minutes officially.
12 minutes officially, okay. Let's see how we go.
We have a bit more.
Okay, that's fine. Okay, so this is one thing that my colleagues at Meridian came up with, just to provide a basis for actually analyzing what an upmixer does to 2 channels. So essentially what we have on the left-hand side, the first 2 plots show a sine wave, a sine sweep through all frequencies that starts off in the left and gets lower and lower and lower in the left, gets higher and higher and higher in the right. Okay, so the idea is that it's sort of the sweeps sound like they're moving from one side to the other. And what we can then do is run this through an algorithm, or indeed an actual black box upmixer, and see what it does. So in the case of Kraft and Zolzer, what we can see is we've got, on the right-hand side, top right, we've got left, right, and center. Seems to be pretty sensible, right? So we've got the sweeps just running nicely from the left-hand side. The center gets louder and louder and louder as it passes over that region and ends up in the right channel, okay? So we've actually got extreme panning here. There's a lot of similarity between Midside and Kraft and Zolzer, except that we have the whole active arc to play with now, okay? The second set of sweeps, so this is bottom left, this is where the phase changes. Now you can't see that, so they just look like big blobs, apologies. But at this side, the 2 sinusoids are out of phase by 180 degrees. They then proceed. In the middle, they're exactly in phase, proceed again, and they're out of phase by 180 degrees, okay? And what we see is that when the signals are negatively correlated for Kraft and Zolzer, entirely negatively correlated, they're just sent to their respective channels, left and right. But as the correlation starts to increase, and this is what you would hear, the sound starts to come more towards the center. So if we think about 2 anti-phase sinusoids coming to a point in space that's equidistant, i.e. the center, we expect nothing. And that's what we're seeing. When they're fully correlated, we expect to have more. And again, that's what we see in the middle there. Making sense? Okay, good. Now, let's have a listen. Thank you, sorry. I totally freaked out because that happened as soon as I put that there. All right, okay. Now, we've had a look at the signal models. The premise, the idea is that we start with 2 channels, make some assumptions, reduce a system of equations, and we wind up with 3 channels. All right. Now, we can do this for every time frequency slice, and this is what I've done here. In terms of the sonic considerations of frequency domain processing, we have a few things to take into account. We have the frame size, that's how long in samples each time frame should be before we apply the Fourier transform. We have the number of Fourier coefficients that we actually use. I've set that equal to the length of the frame, just to have, well, it makes things a lot easier. And then the amount of overlap that exists between successive frames, because we don't want to window a slice and then go all the way to the end and window again. We want to have some continuity between the 2 frames. So an overlap of 75%, that means that you're hopping on 25% of your frame length each step. It's mooted as, having a good amount of consistency. I've also used a Hanning window, a periodic Hanning window. This just avoids any non-zero crossings that would lead to artifacts in the resulting signal once you come back. I window on the way into the frequency domain and on the way back out, okay? So, hopefully, this is the original audio. So this is going to be stereo, okay? And very loud. Sorry. How are we doing? Whee! All right? Okay. It's very loud. Sorry, should I dial back on my end? I can't. I'm out of control. Sorry. I'm just gonna go ahead and I can't do anything. I'm out. It's game over. Is it still gonna be that loud? We don't know? No, it's not. Okay. And that was it. Okay? So that's our excerpt. That's the 2 channels. What I'm going to show you is the center, left, and right extractions. Now, what will happen is the center will be nice and dry, hopefully. The left and right will be more ambient. Okay? So this is using the Kraft and Zolza approach in the frequency domain. Now, to start off with, I'm being extremely unfair. I'm using a low resolution FFT here. So I'm only using 1024 samples. They recommend 2048 or higher. Okay? So, hopefully you'll be able to hear. Okay? So, slightly muddy, but not a bad sound at all. Okay? Let's have a listen to the left-hand side. Did anyone listen to MP3 when those were, yeah. So you get that kind of washy, sort of chorusy kind of sound coming through. And when we're wanting, because that is actually going to end up coming straight out of a speaker, and you're trying to widen your listening area. So if someone's sat near to that speaker, I mean, yes, these things are going to sum in space. That's always, we need to take that into account, is that this would never be listened to in isolation. However, when we're aiming for high fidelity, we don't want this stuff in our signal, okay? So if we just stick, knowing that the center sounds pretty good, we just stick with the ambience and then just raise the resolution of our short-time Fourier transform, things do get better. chorus in effect, but it's not as rapid as it was. So it sounds ever so slightly more stable at this point. Now, because I'm probably going to be in a bit of a rush, I'll just show you the highest fidelity one that I have rendered. Instead of having a sort of weird chorus effect, now it almost sounds like a sort of really, really fast delay, sort of grating sound. Okay? Sorry?
Except on the cymbals.
Except on
still swooshy.
it's still swooshy. Okay, thank you very much. The more input, the better, by the way. This can lead to a good discussion. Okay, I'm going to skip this. This is Vickers. To be honest, right. So we saw the objective analysis for Kraft and Zolza. Same story here. How am I doing for time? Like 5 minutes? Or? Yeah, 5 minutes. Okay, cool. Apart from the coherence, the correlation. So when we run the phase sweeps through the Vickers approach, because we're dealing in the frequency domain and we're relying on things like correlation, we actually end up nulling out the center channel for completely out of phase, which is fine. But we also null out for 90 degrees. We had a condition that said left and right are uncorrelated. That's baked into one of the assumptions. So when they're maximally uncorrelated, i.e. 90 degrees out of phase, nothing happens in the center channel. For real program material, this doesn't seem to cause an issue perceptually, okay? All right. So what does Vickers sound like in comparison? For the center extraction, it's seriously good for vocals, but you'll hear an artifact.
I don't ever want to die, want to be immortal. I'm so thirsty, let me drink your water bottle. I don't ever want to die, want to be immortal. I'm so thirsty, let me drink from your water bottle.
Okay? But the vocals, that was pretty, apart from the little kind of MP3 whistle in the background, the vocals were really good. So if we just dial up the resolution again, so again, I'm being extremely unfair. That first example was 1024 frame size. Vickers actually recommends 4096 or 8192. So I'm going to play you 8192.
I don't ever want to die, want to be immortal. I'm so thirsty, let me drink your water bottle. I don't ever want to die, want to be immortal. I'm so thirsty, let me drink from your water bottle.
Okay, so Vickers definitely knew what he was on about. Like that's cleaned it up massively. Again, we get swooshiness on the cymbals, a very slow phasing effect. However, the vocals sound so much cleaner. Right, now the actual crux of the matter. Moving into the time domain, I've summarized it as thus. So, Kraft and Zolza, massive inspiration for this work. They actually did this with their own upmixer. So the one that you've just heard prior to the last one, they said, right, okay, well let's see if we can do this in the time domain. So we create a complementary set of filter banks, so that provides a really well-behaved graphic EQ, if you like, to split up into the frequencies. So as opposed to doing the Fourier transform with different frequency bins, we now have big bands of stuff that we can then analyze in the time domain. And we analyze it through time averaging. So if we're wanting the power of a signal, we would simply say signal squared and then exponentially smooth the value over time. Now, this isn't the be-all and end-all. It's just one approach. There's probably better approaches out there because ultimately you do end up with a little wiggle in these average readings, which we're wanting to overcome. Now, do you get the same results? Absolutely not. They sound really quite different, okay? So if we cast our mind back to what we heard with Kraft and Zolza's upmix in the frequency domain, I've actually got them here down at the bottom for reference. But if we just go ahead and listen to the center.
I don't ever want to die, want to be immortal. I'm so thirsty, let me drink your water bottle. I don't ever want to die, want to be immortal. I'm so thirsty, let me drink from your water bottle.
Okay, sounds okay, sounds quite smooth, reasonable. However, there's an issue because I've used a very small exponential smoothing value here. So this is how rapidly the parameters that I'm throwing into the upmixer are actually going to update. The more rapid these updates, the quicker the fluctuations, the more distorted the sound becomes, and it actually harms the extraction of the ambience in particular. So instead of having phasey washy issues, we've got a different problem now. We have a sort of a pulsing, a chuffing kind of effect, and ever so slightly, something verging on soft clipping maybe, right? Something like that. But if we then say, okay, let's just calm down how quickly these parameters are updating. Let's just smooth out the averaging a lot more. Can we get a better sound? Okay, so it still sounds a little rough around the edges, but if we compare that to the original frequency domain, which would you say is more objectionable? The last one. Okay, so the time domain is definitely doing something that we like a little bit better. So maybe. Do you want to hear them again? We're probably not yet convinced. We'll do Vickers now, because this is kind of, oh, hang on. There we go. Okay. So I didn't actually show you this, but this is Vickers ambience extraction in the frequency domain with a high resolution. This is as good as it can get, okay? So we've kind of got the worst of both worlds there. We've got a bit of phase, and we've also got, that sort of gruff kind of distorted sound. But I'll play you one more. This is the biggest part of the presentation, actually. It's the fact that Kraft and Zolze took their own approach in the frequency domain to upmixing, stuck it in the time domain. We've gone through it all. We've actually managed to listen to it. You've all listened to it today, which is great. It's something that, as you say, you don't really get to do at conferences. But the cool thing is that you take the same paradigm or approach, and you can apply it to any upmixer. It's great. So we took Earl Vickers' approach and stuck it in the time domain. And compared to what you just heard, you get this. Okay, so more coming and going in terms of volume, level of the direct sound, if you like. That's tunable with the alpha parameter for the exponential smoothing. It's not, again, this is actually something that's down as future work. It's very ad hoc, the tuning of that particular parameter. Anyway, I need to shut up. So if you want me to play anything more, please do let me know. We can always come back to this. I may or may not even bake off some 2 to 3 actual upmixes. So you can all not hear what you've just heard because it's all mixed together in space and you go, what's the problem? Okay? Any questions? Or I don't know whether you have time.
Perhaps one question.
One question. Go on, please.
Do you think if you were to use data that hadn't been multi-band compressed to begin with, some of the artifacts might be less apparent?
Yes,
I
definitely.
think pumping as it distributes power.
Yes.
Being exposed.
So what you're saying, like if things weren't so hard limited, or
I think it's the way that it's been mastered.
the way that's actually, okay, it's a program. We are finding that it is, some of the tuning, especially for the exponential smoothing of the parameters, is or can be program dependent. There are particular delay values associated with the parameter that you can sort of tune in. Like the one that sounds best corresponds to a few milliseconds, for example. In terms of the way that the material is actually put together, I'm not sure, because this track was actually a university submission, and it's a band that are playing at Glastonbury. So if you're going to Glastonbury, definitely check them out. We're called Gaffer Tape Sandy. That's a shout out for the stream because I probably don't have royalties for it. So there was actually, as far as I know, there wasn't any multi-band compression on that particular track. So who knows? And it raises a very salient point in that. Is there one? There's never going to be one solution that's going to work for everything. So what you've heard today, you could put X number of other tracks through it, and you get perhaps a different result, or well, not massively in terms of the type of artifacts you get. Are they less noticeable, or are they larger? So in summary, I don't know. I think
Measure the spectral flux before and after.
the spectral flux.
Yeah.
We need to talk. Okay, thank you very much. Really appreciate your time.
Okay, thanks, Stephen.
Cheers.
Okay. Brilliant. Thanks. Can grab that. Well, dare we fire up another PowerPoint? Let's see. There we go, full screen. No, we don't dare go full screen. Okay. No. There's something happened when switching it over that we will investigate at lunchtime and sort out, hopefully. But just try going backwards and forwards on that. Yeah, that'll do. Brill. Okay. No. Make it a bit smaller.
I think it's all right.
Yeah? Just need some grey. Let's keep going. Okay. So our next talk's up from Adam Hill. And Adam's a senior lecturer here at the University of Derby, where he runs the MSc Audio Engineering program. He received a PhD from the University of Essex, an MSc in Acoustics and Music Technology from the University of Edinburgh, and a BSc in Electrical Engineering from Miami University. His research generally focuses on analysis, modelling, and wide area spatio-temporal control of low-frequency sound reproduction and reinforcement. And Adam also works seasonally as a live sound engineer for Gandhi Concert Sound, where he has designed and operated sound systems for over 1,000 artists. Adam is also co-chair of the AES Technical Committee on Acoustics and Sound Reinforcement and head of the content for the Electroacoustics Group Committee of the Institute of Acoustics. Adam's going to talk to us about sound exposure and noise pollution. So without further ado, Adam Hill.
Great, thanks Bruce. I guess I'm what's standing between all of you and lunch, so I'll try to keep the time as much as possible. What I'm going to talk to you about today is part of an ongoing project within the AES that's been happening since very late 2017, where we're at the point right now where the work we've been doing has culminated in a report that's about 50,000 words, 130 pages right now. So last week I gave an AES IOA presentation on this into an hour and a half, which wasn't enough time. And so now I'm squeezing this into half an hour or so, which is definitely not going to be enough time. So you're only going to get a very small glimpse of what this project is doing. But I've tried to weed out maybe the finer points of what we're doing and really focus on the major things and the major messages that you should at least go away with. But just out of interest, how many of you in the audience are involved in either designing systems or operating systems? Show of hands. A few of you. How many of you are performers? A few of you. A few more. How many of you attend music events? A few more of you. And how many of you live near a live music venue or an outdoor music event site? A few more of you. So I think we've covered just about all of you. So this sort of thing really covers pretty much everyone, or at least the vast majority of people. So it is important, which is why we're looking at it. So the general focus of this group was to develop a set of recommendations outlining what needs to be done to address the issue of sound exposure and noise pollution due to outdoor entertainment events, with an emphasis on practicality and preservation of a high-quality audience listening experience. And there we are. The key here, and this is talking to the various members of the working group, is that no matter what we do for making sure we have a safe audio experience and not annoy the neighbors, we can't detract from a high-quality audience listening experience. At the very early stages of this group, Bob McCarthy from Meyersound was very much involved in this, and he emphasized this over and over again. Whatever solutions we come up with, the audience can't be negatively impacted. That's really important, and that's something, especially on the noise pollution side, that previous groups who have attempted this have ignored. They simply look at noise pollution and say, what can we do to limit that? We're trying to look at the big picture here and to make everyone happy, which is why the presentation title is called Threading the Needle, because as we're finding very quickly, this is easier said than done, not even easily said in some cases. So anyway, we officially formed the group in March of last year. I finished the initial draft report this March, and just last Monday, we released our second version with the aim of this being publicly released by the AES probably autumn of this year, if we can get everyone to agree on it. We'll see. Contributors, this is always in a state of flux. This is where we stand at the moment. So we have Duran Begalt from Charles M. Salter Associates out of San Francisco in the US. He also does quite a bit of work with NASA on noise exposure for the astronauts, which actually has fed quite a bit into this work, believe it or not. We have Etienne from L Acoustics, who I'm sure many of you will know quite well. We have me. We have Joss Mulder from Murdoch University in Australia, where he's actually in the middle of a major piece of research looking into small music venues and noise exposure to audience members. We have Elena from D&B, John Burton, freelance engineer in the UK. Again, a number of you may have come across John in your work. We have Christian Frick out of Rocket Science in Switzerland, Marcel Koch out of DB Control in the Netherlands, Kees Neervoort out of Event Acoustics, also in the Netherlands, and Andy Wardle, who's at the University of the Highlands and Islands, way up in Perth in Scotland, but he spends his summers effectively monitoring noise at major music festivals, so a huge amount of industrial experience there. So interesting group of characters, but everyone on this group is kind of coming from a slightly different place in industry, which makes for some really interesting discussions and some fairly heated debates at times. So that's who's working on this. Now, I've highlighted kind of the key questions that have come out of this. We're not providing many answers right now. We're providing some suggestions, but really this report is a critical analysis of what's out there already and what's been done. So at present, there's 25 questions that can be broadly lumped into audience-related questions, community-related questions, and engineer-related questions. So I'll go through a few of them from each category here, but just keep in mind that this is only the tip of the iceberg with this project. There's going to be a lifetime of work coming out of this. I think I was just talking with Joss Mulder the other week. He came to visit. And to be honest, I think if we're optimistic, we'd say we'd have a significant change within 20 years. This is a long-term project. It's not going to change overnight, these things, but you need to start somewhere. That's what we're doing. So for audience-focused questions, the first key question, at least from our group, what we think is, what is an appropriate sound exposure limit to the audience? Now, we've sat down and gone through all the regulations in the world. That's both for environmental noise and for on-site audience limits. And for the audience, we're doing comparatively well in Europe and the UK. There are limits in place. They don't agree with each other, but they're there. Where I do my work in the US, it's pretty much a free-for-all. We don't care about the audience very much as long as they're paying their ticket price and they're coming in. There's not much concern beyond that. But focusing on Europe, I think there are some good things to take out of it. You won't be able to see that graph because the screen is shrunk. But basically, it's a compilation of all the current audience limits in Europe. The interesting thing is that the primary limit on all those is A-weighted, which if you're looking at a typical audience exposure at an event, it's round about 100 dBA, which if you know anything about equal loudness contours, you'll know that A weighting is not appropriate. But everyone's using A weighting. we're stuck with it for now, although this group is not necessarily recommending carrying on with that. But the interesting thing about that is all of them are roughly based on the WHO recommendations from 1999, saying that 100 dBA over the course of the event is what's allowed. So roughly talking about 4 hours. Some countries have taken that 100 dBA limit and said you can only use a 1-minute integration time. So 100 dBA over 1 minute as compared to 100 dBA over 4 hours is extremely different. Right? The 1-minute version, you're going to have to mix much quieter than the 4-hour version. So we don't have agreement even within Europe. And their starting point was the WHO guidelines from 1999. I think interestingly, those of you who pay attention to these sort of things, last year the WHO released their community noise guidelines for Europe. And it was broadly split into traffic noise, I think industrial noise, wind turbine noise, and leisure noise. In the leisure noise section, they said, well, we've gone through everything that's been published in this area, and all we can find is a collection of highly biased, unscientific pieces of research. And they basically said, we can offer no further guidelines to what we said in 1999 and a bit to the night noise guidelines in 2009. They said someone has to go out there and do some proper scientific research. And that's largely what we found in conducting our literature review for this. There's a lot of biased research out there where it's clear that they started with their conclusion and then tried to craft an experiment to support that conclusion. So we're not really in a good place. There are some secondary limits that are DBC, which are generally in line with occupational noise limits, peak limits. But again, there's very little agreement between countries. So certainly some work to do in that area to try to figure out what is a reasonable audience exposure limit. Building on that, and this has really been my big point going through this work, is the question of are audience members and staff situated near ground-based subwoofer systems receiving dangerous noise doses? I've been designing these systems since I was a teenager, and it just, well, since we started using line arrays, it seems to be the way to go for most systems. Put a line of subwoofers on the ground, you'll have the subs here, crowd barrier about here, and then, well, a sea of people in front of that. And I never thought about it until I did this work, that, well, wait a minute, what are the people in the front rows being exposed to? I could be standing here listening to the show where I can reach over the barrier and pretty much touch the subwoofer. If you look at what some of the large format subwoofers can put out, you're talking roughly 100 dB peak at 1 meter, 140 dB peak at 1 meter. Some of them go louder than that. That's peak, so that's the most they can put out, so they won't be hitting quite that much. But I mean, just consider what you're dealing with a big festival or stadium show. We just did some work with John Burton and the Prodigy for their last world tour. Their subwoofer array, I think there were 72 subwoofers in it, and it was about 30 meters across. That's significant sound pressure levels that you're delivering to, well, audience members a meter or so away from the subwoofers. And those are your best audience members. They're queuing up to get those spots. And they'll be there for multiple shows during the tour probably. So I don't think it's safe, and I think we need to think again about why we're putting these subwoofers on the ground. Speaking to Elena at DMB, we both agreed that we can totally geek out about the beam steering, and the physics behind playing with these subwoofers, but I just think it's dangerous. Have you ever stood there during a show being pummeled by bass? It's not a very good listening experience. Your teeth start rattling, you can't really see straight. It's just not nice. So L-acoustics especially have been really emphasizing over the past year or so flying your subwoofers instead. And we'll get to that in a little bit, but there's of course drawbacks to that. But I think if anything comes out of this report in the long term, it might be to move away from ground-based systems, just from not only a health and safety point of view, but the fact that if you have, 100 meters at an extreme of audience members, if you think about the distribution of sound energy between the front and the back, there's probably about a 30 dB difference in the low frequency. So you're not getting a consistent coverage over the audience. So not only a health reason, but actually a consistency of listening experience you're not achieving with these, even though they're much easier to just roll off the truck and park in their position. Tied to that, you'll start to see a theme emerging. Does standard hearing protection available at events, so typically the foam earplugs that you'll see, well, a lot of the concert goers, certainly the security guards have in their ears, does it do anything to protect from these low frequencies that you're being exposed to? One of my colleagues, Ian McKenzie, he specializes in bone and tissue conduction. So I asked him in the office one day, because the idea popped in my head, are these foam earplugs doing anything for this level of low frequency? And he said, absolutely not. It doesn't matter if they're in your ears or out. That sound is getting to your inner ears. It's going to travel through your body. And he gave me the example and sent me some research papers based on deck crews on aircraft carriers, where they're exposed to similar sound levels, probably longer duration and slightly higher intensity, but a lot of them wear full body suits, so no skin is exposed, so there's no acoustic path to get to their ears. And I'm not saying we give audience members full body suits to go to shows, but what I am saying is that thinking that foam earplugs are going to solve the problem is horribly misguided. Think about security guards. If the audience is standing here, where are the security guards standing? They're standing here, and they're there all day. They're being paid to do it, so they should be covered by occupational noise regulations. And we give them foam earplugs and say, oh, there you go, you're protected. They're not protected, no way. So this is a serious consideration. If you look at the NASA documents for this, where they're looking at similar exposure levels for their astronauts, they say, under no circumstances, if you identify a noise exposure at that level, which are the levels we're talking about at events, under no circumstances can you use earplugs. Something else must be done. So something else needs to be done. What it is, I don't know. I think a starting point, again, is putting the subwoofers in the air. That will solve a good chunk of the problem, I think. Community-focused questions. So we're moving away from taking care of the audience members. In the community, what's the most accurate and practical method for predicting noise annoyance in the community? Looking at the literature on this, there's no consensus. I mean, depends what paper you pick up, you'll get a different idea of what's annoying to people. So there's a lot of suggestions out there. One that comes up quite a bit, again, we're looking at low frequencies. It's usually the thumping of bass from a nearby event that tends to be annoying. High frequencies can be steered quite well by systems these days. It's only weird atmospheric effects that'll cause extreme propagation there. But a common one is if you have a greater than 20 dB difference between dBA measurements and dBc or unweighted measurements, then you're likely to have a problem with low frequency annoyance. Also, digging through the literature, there is a model developed by Zwicker a number of years ago that seems to be a very detailed annoyance model. So it's looking at the loudness of a noise, the sharpness, the roughness, and fluctuations in strength, all tying into a way to predict annoyance. In the various bits of research that have tested that model to see if it works, it does tend to hold up quite well. The pushback is that people doing noise monitoring for these events say, well, I can't deal with a model like that. It's too complicated. I like to have my sound level meter, and it gives me a number, and that's it. So there's resistance to taking on anything that's maybe too difficult to grasp. Relative duration and level, that was a NASA study. Basically, they did a test on annoyance, exposing people to, I think it was 78 dB over I think it was 18 seconds of noise, followed by silence. They said, how annoyed are you by that? And then they did the same exact sound, same level, followed by a significantly quieter noise, I think at about 60 dB for the same duration. The people who had the quieter noise directly following the louder noise were significantly less annoyed, which is interesting. I'm not sure how that exactly ties into event noise, but it's something to at least consider. Absolute C or Z weighting, that's coming up quite a bit and is being pushed by Marcel Koch at DB Control in the Netherlands. He's actually doing his PhD on this at the moment, where he says it's not perfect, but it's certainly an improvement over A weighting because it captures the low frequency energy that tends to be the annoying bit. But our problem at the moment is that there are a lot of people who swear by using A weighting for environmental noise monitoring. There's some major reports that were done through DEFRA in this country a few years ago that say in, well, actually fairly uncertain and simultaneously certain terms at the same time, that absolute A weighting is the only way to go for noise measurement in terms of annoyance. And it was clear to me that these reports, there are two of them, they were done specifically to prove that A weighting is the only metric you need to consider. But within their summary of the second report, one paragraph says, the results are inconclusive, the data doesn't point to any one metric. And in the very next paragraph it says, the conclusion of this report is that there is no shadow of a doubt that A weighting is all you need to use. And this is supposed to be the report that's guiding our industry on concert noise. So we have some issues, and that's one of the things I suspect is what led the WHO to say we need some proper research on this because it's not out there right now. Just to highlight one very interesting study, this was done by the Danish Environmental Protection Agency in 2002. They tested annoyance for the general public on a range of different noise sources. And they found that the two most annoying noises that you can be exposed to are, number one, a drop forge, and number two, music. Everything else was very much further down the annoyance scale, but the drop forge and music were right up there at the top as extremely annoying. Again, this largely pointed to a lot more research needing to be done, but it gives indication as to how annoyed people can get. I should note that what we're dealing with here are events that only happen a few times out of a year, whereas a drop forge, if you live near a factory, is happening throughout the year. So they're maybe not directly comparable. But if you live down the street from an indoor venue, that could be happening year-round, in which case, yeah, you're going to want someone to do something about that. On a non-measurement side of things, this is actually something that we are in agreement on, and I haven't seen anyone say otherwise yet. Communication is essential in terms of annoyance. So Vanguardia in the UK, primarily with Jim Griffiths, they found that a targeted communication campaign before a large event happens in the community, so they tell all the residents that this event's happening, brace yourself. That process and giving them a noise hotline to call during the event actually significantly reduces annoyance to the point where there are very few complaints. And it's something that's come up in NASA's research, that having a perceived control over an annoying noise source actually makes it less annoying. Even though that hotline might be going to an operator who says, yeah, I'll pass it on to the mix engineer, maybe it doesn't go anywhere, but it's the perception that counts. And DB Control has found the exact same thing in the Netherlands. They've created a new position that you can hire in for events called sound guards, where their job is to communicate between all relevant stakeholders, between the community and the audience and the mix engineers, the system designers, the musicians. They talk to everyone. And they found that having a clear, non-technical communication method between most people solves most problems and makes for a much more smooth running event. So communication is absolutely key. There's no gray spots here. This is something that we can make a clear recommendation now, that you need to communicate with all members involved about this. Standardization of noise monitoring practices. I'm not going to say much on this because I'm sure I'm running out of time soon. But this is again from Marcel Koch at DB Control, where he's saying a lot of events are in phase one right now. The ones I work in the States are absolutely phase one, where they don't tell me, you can't tell me what the limit is until about halfway through the first song of the first band on the festival. Well, the last time I did it, they said, okay, 90 dBc fast weighted, that's what you can have. And I turned off the PA and it was still above that. So that's what's happening in the States. They're very far behind, but this is something that goes back to the 70s, reasons for that. But really, we want to move towards something that has full transparency for both the community, audience members, musicians, engineers, everything. They can see the data, they can see what's being done to essentially make them happy. And really just there's no kind of man behind the curtain. It's all out there in the public, and that's where we're pushing, what we're pushing towards. Rocket science, they've developed a product that actually can go in someone's bedroom or living room to try to counteract the annoying low frequency noise. Put that in there, it monitors the noise that's coming in and tries to cancel it. They haven't been able to provide me with data yet to prove that this works, but they have some kind of informal feedback saying that, yeah, they've deployed this in a community near a music festival in Switzerland. And, well, again, it's hard to say if it's a subjective thing or actually objective, but annoyance has gone down. You might just think, well, this special box is in here, so I'm less annoyed. Anyway, this is what I was talking about. These are engineered focus questions with L acoustics. Just a quick note saying that, can we achieve a better solution for audience coverage with flown arrays? I think the answer is yes. This is a ground-based system. This is from L Acoustics AES paper from last year, just showing, well, we have in this case, I think, upwards of about 20 dB difference from the stage, which is here, to the back of the audience, which is here. And if you manage to get a flown center array, which is easier said than done, you can get only just touching 6 dB difference from front to back in an audience. That's over 60 meters. Not only that, you don't get any of these red spots here, which really are the danger areas for noise exposure. It's nice, even coverage, and you have control over the overall audience exposure limit. So I think the outcomes from this report we will be recommending to try to go to flown systems. And I realize that this comes with it, takes extra time, extra rigging. You have to negotiate more with the lighting and video people. But I think from an audio point of view, it just makes sense to put in that extra effort. We'll see. Also, I think virtual bass could be a very useful tool for limiting annoyance offsite. This actually is from Event Acoustics. They have a tool called Bass Creator, which they actually stole some of my work when I was doing my PhD and put it into this without telling me. Now Keys is part of this group, and yeah, he said, oh yeah, that's from your PhD thesis, sorry. But my thesis, I was looking at notching out problematic room modes in a small room. So if I can't correct for it physically, I'll notch it out of the system and replace it with virtual bass. So it's a psychoacoustical effect where you add a higher harmonic series, and within your brain that replicates the perception of low frequency to a point. They're doing the same exact thing but in the community. So if they say narrow band around 63 hertz is causing annoyance, we'll notch it out of the system and replace it with virtual bass. So on site, the perception is maintained as long as you don't overuse it. If you overuse it, it sounds horrible. But within reason, the perception is maintained, while off-site, you've lost your annoyance issue because physically that frequency is gone. So I think this is a relatively new unit. And again, there's no data out there to actually show its effectiveness, but they are pushing this, and I think it's a very interesting approach to this problem. Extending system bandwidth. This is the subject of John Burton's EMRAS dissertation from University of York about 3 years back, where he uses a DMP system. This system shots actually from one of his older tours where he insisted on using an L-acoustic VDOS system, which he was since banned from using because all the riggers absolutely hated it because it's just not a modern system anymore. But he used a DMB subwoofer array. So you can see it starts here and goes way over there. So it's extensive. This is for the Prodigy. But his experiment was simple. He said, okay, I'm going to do 2 trials. First trial is you have only standard bandwidth subwoofers. So typically they're going down to about 30 hertz. Then the second trial, I'll include infrasubs. So these will go down to mid-20s, low 20s, something like that. And what he wanted to see was what are people's preferred playback levels between the standard subs and the infrasubs. So he had a single dial at front of house, no labels on it, no nothing, and had all the members of the technical crew set their preferred playback level. And what he found was that when you extend the bandwidth downwards, it's not in the infra region really, we're still in the 20 hertz region, but when you extend it downwards, their preferred playback level is lower. Now, in some cases, this was only lower by maybe 2 dB. In some extreme cases, you're looking at 10 dB lower in low frequency level, which I think is fascinating. And he's the first person that I've seen actually at least publish on this. So there's this question, can you trade off bandwidth for output level? It seems that you can, but I think, well, John will admit there's still a lot more work that needs to be done in this area. But even saving a few dB off-site, that can make all the difference between a really annoyed community and a not annoyed community. Getting to the end here, how effective are secondary sound systems? So rocket science are doing a lot on this, as well as the Danish Technical University as part of the Monica project. But basically, there are a secondary system of subwoofers on the perimeter of your event site, where the whole idea is to cancel low frequency energy from going off-site. So this is one of them in all their glory. This is courtesy of Christian at Rocket Science. Their experiments have shown that this works, and they've deployed this at real festivals for a number of years now. They get about 10 to 15 dB reduction off-site in the low frequency band. And what's coming out of DTU is very similar results. The problem they encounter is that the neighbors who live by this and see them setting up a massive wall of subwoofers right across the street, they freak out and they're annoyed before anyone turns on the sound system. So again, it's a communication thing, it's a perception thing. But I think it's really encouraging what these systems are able to do. Although I asked the question, well, what happens if there's a high rise nearby? How do these deal with height? And kind of shrug their shoulders like, well, we didn't think about that. It's only looking at the ground, which maybe is an issue. But I think it's an interesting potential solution to this. So we do need to look into this a bit more and do some proper scientific research on it, which luckily DTU are doing in the Danish Technical University. And lastly, last question here is automatically mixing to the sound level limit a real effect? This is coming off of Joss Mulder's work in Australia, where they've done a long-term study in music venues where half of the nights they'll give the mix engineer view of a noise monitoring or level monitoring bit of software called 10easy, where they say, okay, this is your limit, you have to mix to it. The other half, they don't show them anything. And they wanted to see what the effect that was to try to limit noise pollution really off-site. Without monitoring, each little dot was a different night in their study. With monitoring, again, each little dot was a night in the study. And what they found was that when you have sight of noise monitoring software, all of a sudden all the levels squeeze up to the limit. Now this is good for really loud mixes, because that'll keep them within their allowed value. But the unintended consequence was that the softer mixes actually came up to the limit. And shockingly, on 10easy's website, there's a testimonial from one engineer who mixes a soft rock band, saying, this software is great. This helped me be the loudest band in the whole festival. Like, do you really want to be the loudest band in the festival? It's not appropriate for your music. But this was, well, a bit concerning, I know, for the researchers involved. And they're actually thinking right now of a way to change the user interface so that it doesn't encourage people to mix to the limit and more mix to what's appropriate. But, well, if you have any ideas of how to do the interface, I'm sure they'd love to hear. But yeah, they're struggling with ideas right now. A few ideas, but nothing that really seems to be, well, to stick at the moment. So anyway, we're doing a case study at a big music festival that I work with every summer in Chicago. And we're going to try this out on a large scale now with a 50,000 person music festival to see if this effect is the same. So kind of watch this space. So to sum it up and release you for lunch, this is a challenging area. I think there's no other way to say it. From an audio engineer's point of view, which is what we are on this committee, we're not acousticians, we're not environmental specialists, we're audio engineers. We have two roles that we have to meet simultaneously. First role is design a sound system that delivers uncompromising, consistent, high-quality audio to all audience members. Okay, that's been more or less the same for 40, 50 years. And it was only really within the past couple decades, I'd say, that we have the technological means to really achieve this. But we also have this goal of limiting noise pollution, which is related to annoyance in the surrounding areas. How do you do both simultaneously? That's the question. That's ultimately what we're getting at here, on top of protecting the audience members from significant hearing damage. So I'll end on a quote. This isn't a new quote. This goes back to 1980. It appeared in the Journal of the Audio Engineering Society. But I think it kind of hammers home how little we've moved since 1980, so nearly 40 years. It says, our civil liberties will be eroded by any government dictation or control of our leisure lifestyles, but this intervention can definitely occur sooner or later unless an aroused citizenship assumes the initiative to counteract the tidal wave sweeping our civilization into the insidiousness undercurrent of oral incapacitance. It is hoped that the profession can hear the whispered hint if it is not yet deafened into insensibility. I think that's still where we stand. We have to be careful. There's already government regulations out there that are ill-informed and not fit for purpose. We need to do something, and I think we need to start now, hence the point of this group. So I'll leave it there. Maybe time for 1 or 2 questions, but if you want to get in touch, that's my website, and UOD Live is our subject group website here. So thank you very much.
Okay, we're running a little bit late, so what I'd ask, if possible, is if you could take your questions to the dinner room, which is MS005, if that's okay. And we're going to be aiming to be back here at and composer of music for computer games, theatre performances, film and multimedia. Author of spatial sound installations. Is a musician, multi-instrumentalist, music producer and DJ. Research and teaching assistant at the Department of Sound Engineering at the Frederick Chopin University of Music. Creator and curator of Permanent VR Projection Exposition, UNFC VR. And he's also a PhD candidate in the subject of sound design for 3D space. But before we start, actually, is Patricio here? No. In which case, you might have longer than half an hour.
Okay.
Because that name badge is still there.
Okay.
And they're up next.
Okay.
So, well, they've got half an hour. So, we'll see how it goes. So, without further ado, I warmly welcome our next talk. Played over hardware generously brought by Dallas Simpson, who we'll use again tomorrow. Like I say, feel free to play around with audio levels while it's going. And over to you.
Thank you very much. I'm very pleased to be here. So thank you, Bruce, for inviting me. And I would like to present some of my achievements in the space of producing immersive music documentaries. And this is a very important topic for me because I believe that every technology needs to be publicized widely. So everyone should use this technology to make this technology live. And I fell in love some time ago in VR technology. And I'm very afraid that this technology will die. So I'm doing everything to make it live. And how it happened and how it goes, this is what I'm going to be talking about. So basically this is my 1 year and a half of experience doing recordings of concerts, musical concerts, with 3D cameras and Ambisonic microphones. And I was looking for a methodology to produce such documents and present them. So I was interested not only on recording, but on the whole workflow from recording, authoring, and then presenting those documentaries. But what is my background? My background is that I'm a performer. I am educated as an oboist, so I played a lot in orchestras, chamber ensembles, and in different places, with different conductors. So I was so used to be on the stage that when I was listening to the music, I usually flipped the stereo to have violins on my right side. So this is maybe important in the later part of my talk, that I place cameras on the stage. I was also studying with Fine Arts Academy multimedia workshop, where I learned about using different techniques of visual art. So this is also a place, the Fine Arts Academy, where I started to produce documentaries about music, typical documents for TV. So that was the place where I was interested about showing music on the screen, which is not an easy thing. I have also experience in gaming industry. I made some music and sound effects for games. So I learned about game engines, and it happened that game engines are the best authoring tools for VR now. So I use them for my documentaries. And why VR? And this is something fun, because in 1992 I saw a movie. I was in my primary school, and I saw a movie made by Brett Leonard called The Lawnmower Man. And it was based on Stephen King's novel. And when I saw this movie, I fell in love with VR. I felt that this is something that I need to learn about and learn how to use it. And I didn't realize that in Banff Centre in Canada, artists were experimenting at that moment with this technology. And one of my colleagues from the university was a PhD student at the time at the Banff. So when I started to learn about VR, she told me, I was there in the 90s, and she told me all about it. So I wanted so much that for 20 years I waited until the first headset that was made by Oculus, not the development kit, but the consumer version, was put into the stores. I bought it, and for next month I was in VR all time. And I watched everything that was available. So I learned also about the cyber sickness, the virtual reality sickness, that there is something like this, and it's not something that we will easily forget when we are producing the long music documentaries. We need to adapt it. So I got the knowledge about the VR at the moment, and I started thinking about combining all my experiences. My experience as a musician, as a spatial sound installation designer, as a video documentalist, and how to connect it with VR. And I had a vision that many of my students at the moment were making some fine installations, multimedia installations, but they were presented, for example, once at the end of the year. And it was sad because they were good and there was no place to show them. So the documentation is not everything that you is rather everything that you will have after doing such thing. When I was thinking about showing VR things, I wanted it to be open to public all times. So I started thinking how to make it happen. I picked up my favorite tools and started making mock-ups. How should it be presented? And I thought about this booth when you can put a headset and everyone can go into this booth, put headset, and watch those documentaries. And I started to plan it with my colleagues, and this was the first design of this booth. So it was like something like telephone booth, but with some elements of our university's identification. I've made it with guy who is an architect of scenography. And this is the 3D render. So why booth? At our university, there is always noise. Someone is practicing on instruments, people are talking. So if we want to be focused on sound, we need some separation. So this is why I thought about booth. Of course, booth has its own negative features, like it gets hot there, so we need to have some ventilation, and this gives you noise, etc. But maybe later about it. At the back side, you have place for the PC, your workstation, which will play the VR productions. And I always thought about security of people, so we have rails, and people that are not used to be in VR can grab and not fall. And this is the real thing. It is placed in foyer of our concert hall. So each time when the concert begins or ends, people are walking out and are walking to this. There is a light that starts from the movement. So everyone walks out and they see this booth. So they can go inside, put the headphones, put the headset, and start the show. Some students mocked me that this looks like TARDIS. Maybe a bit, of course. So, and Chopin was also curious about it. So, when we presented it for the first time, I prepared material that was 2 minutes long only, because I have only one booth, so one person at a time can watch the material and others are waiting. So the material cannot be long, and we have to remember about abilities of people to watch VR. 15 minutes for me is plenty. So at the vernissage, I try to talk with people, but it is important to think about the space of the presentation also. So when the people are around your presentation booth or something you will produce, you have to think about the space. You can arrange it to make it give best experience for the people. This is Dean of our department, Professor Małgorzata Lewandowska, watching for the first time VR. And as it occurred, VR is one of the most democratic mediums of all. Why is that? Because there is no age limit. I'm not talking about the babies, small babies, but when you have face that fits to the HMD, you're ready to watch it. But there is also no limit. Here's an elderly person with a cane, so everyone was interested. But when you think about consumption of art or high music performers, it is very expensive. It is not common to have many concerts around you. So if you capture such event, you can project it to people for just tiny amounts of money or for free in public institutions and give them access to best culture that is available. So this is the democracy I'm talking about. The democracy of access to the content. This is my team, which helped me doing this event. And those are now photos from the first concert that I recorded with VR technology. It had place in the Museum of Polish Jews History, and they have a fantastic concert hall, but this concert was reinforced in sound. So the sound was everywhere, and I was using experimentally 2 Ambisonic microphones and normal set of microphones for reinforcement. So I recorded everything and tried to make something out of it. The idea was not to make a recording of a concert, but documentary about this concert. So I recorded also interviews with musicians, and I will show you the material. There is such feeling of this documentary. So there was also difficult light environment because we had some, like for example here, not typical light for cameras, and 3D cameras are even more difficult in this means of light. So this is something that we need to work more on. The music was fantastic. I don't know if you have a grasp of Polish music scene, but there is a musician called Leszek Możdżer. He's famous pianist, and he was playing there as a guest musician. So this is for me something that gave me some good vibes. And you have, here is a Zilia microphone. This is Polish ambisonic microphone, 3rd order, the one with the red ring. We had to tape the light because it was not good during the concert. So now I'm working with Zilia, and they made this driver that you can turn off the light. So this is 3rd order microphone, and it is based on MEMS capsules. It has 19 of them. This is my audio team that helped me recording, and this is the video team. So many people were involved in this project, and afterwards, when I gathered all the material, I started to authoring the thing. And what it occurred that you need plenty and plenty of tools to make it happen, really. Because I was trying to use all the sources that I recorded, but it was not easy to base the sound only on the ambisonic microphone. So I needed to use the spot mics, and ambisonics were used mainly to extend the space, the sound of the space. And as I said, this was a very loud concert, so I could use ambisonics and spot mics together because of there were no phase issues with the sound because of the loudness of the concert. And these were the tools that I used for the authoring of the video projection. So the second concert, I picked a small chamber concert without sound reinforcement, just to compare how it will work using the same techniques, spot mics and ambisonic mics. And it was a really good experience. This was a passion concert at our music hall at the university, Baroque music. So, for example, I picked to show you a part where I have 3 performers, and each of those performers is different in tone color, because you have vocals, cello, and positive organ. And they are pretty close together. As you can see, here are spot mics, and here are ambisonic mics on one stand. And I was interested in can I use only sound from the ambisonic microphones? Will it sound good? That was the question when I was doing this recording. And the answer is almost yes. Almost. Why? Because recording with ambisonic mic is something different. You have to have different objective if you use ambisonic microphone, because it records everything. You have no backspace of the microphone, so you have everything. It's like recording with 360 camera. You cannot hide anything. So when someone is on the audience is picking something, it gives noises. If you have noise from the projector, there was a projection on the wall, it will catch everything. So if you I have found it that the best way for me to do such concert is to use the spot mics, but for the restoration of the acoustic environment of the concert, I use the sound from the Ambisonic microphone, but for my hearing only. So I used it to in such way as people on the movie set use recorded sound on the set as a pilot in time. So I used Ambisonic microphone recording as a pilot in space. And what was difficult about it was that this concert hall is very well known for all my professors that recorded there for not 20 years, 50 years. So they know it perfectly. And when I present my restoration, they want to hear this specific concert hall. So you can judge if I made it well or not. We can listen to it. I have 3 versions with me. One recorded with Zilia microphone, one recorded with Ambio from Sennheiser, and the third one is the restoration made with Facebook spatial workstation from the spot mics. I use the frequency delay network reverb from IEM from Graz for making the space. So I will play them, and the real version I have on the headset. So after my speech, I will present it to you. At any time, just approach me and I will show you if you want to listen to it and watch. And now I will play on the flat screen and imitate movement of the heads with the mouse. Okay? Okay, so I hope it will work. Oh. So first is the reconstruction made by me. Reconstruction based on the spatial pilot. The noise is from the mic here. Maybe we can turn it off now? So note this moment when I turn the virtual head to the audience. So on the left ear you should hear the returning sound from the audience. and on the right you will have the natural source from the singer. Okay, now I will show you the version made with Zilia. So this is just plain recording made with this third order ambisonic microphone. I just need to set it up. Okay, now we can switch the microphone. Like, okay, and now I will present you the version made with Ambio. Okay. order, there is a more lack of localization. So you have error of about 30 degree. You can hear all over the singer, the cello. It is not so accurate as second or third order.
So this recording
showed me many problems that are to solve. First one is that the VR cameras use fans for cooling, and those fans are noisy. So you have seen the mics were about 1 meter apart from the camera, and it didn't destroy the localization of the audio. It was something that was okay, but if you would listen to the plain recordings from the Ambisonic mics a bit louder, you would hear the camera noise. The cameras have sync issues. They are developing technology, and dropped frames is not something that is not common in this technology. And the camera distance from the source that you record is also an issue, because you cannot place camera and the audience. You will have just blurry image of the band. So this is how I come to this super spectator position of camera. So you are placed as one of the musicians or some person that stands with the band. For the chamber music, it is not something that is not usual, because chamber music was played in such spaces that people were close to the band. So it works quite nice. It doesn't work for me with orchestra recordings, because I'm not a conductor, so I cannot stand as a conductor. I cannot place camera behind conductor, because it would be awkward to see his back. I cannot place camera between musicians, because in the auditory factors you will have some instruments really close to you, and it won't mix. So this is difficult position. For me, the best position for video recording orchestra with VR is somewhere above conductor, a bit behind him and above. So you have this like from the crane view, something like this. There are problems also with authoring of the material. So how can I prepare such material in a way that it will be easy for everyone to watch it? And there is no such thing right now, because many players that are available on the market won't support Ambisonic at all. The best player that is now is probably Vive Cinema, but it has very clunky interface. It doesn't work from the user experience easily. The easy one is the Oculus Gallery with the HMD headset from Oculus, but it has limitation to second order of the Ambisonics. So if I wanted to make players that are playing audio with the third order Ambisonics, I needed to make my own player in Unity. It was the only way. So I used the Audio 360 SDK from Facebook, and this is how I managed to play the third order Ambisonics. The video quality. In VR, video resolutions are out of space for comparison to the typical videos, because you have, if you want to have stereoscopy, you have to multiply everything by 2. So 4K means not 4K, but 4K for each eye. So you have 4K above or 4K below. You have the square picture, and the resolutions are like 4K by 4K is the lowest acceptable. So this is the bottleneck of the technology right now. You need to implement GPU rendering, which is not also easiest thing to do. So what you can do, for example, if you record smaller ensembles, you have more selective sound. So you need to decide if you will use the spot mics or the ambisonic mic recording, because human voice is like human face in means of distortions. If you see image of human face with a little bit of distortion, you will see it immediately, because it's our brains are so programmed to do so. And exactly the same thing is with the human voice. So every face issues in the human voice, you will spot it immediately. So if you want to test something, if it will work, test it on human voice. What you can do when you do VR documentaries with musicians, you can arrange them on the stage properly for the video and for the audio. So, for example, if you want to have more separation in sound between the voices, you won't do it in post, probably, because they stand on the stage in your video. So you cannot move the voices because you have tied them to the video. So you have to be director on the stage at the rehearsals and at the concert. You have to move them around, tell them that this is how it should be, and this is the moment that you can arrange those things. You won't do it in post. And what I found, that the nicer sounds are when you have arranged it, the voices are arranged in the manner as keys on the keyboard. So higher voices are on one side, and the stage is arranged that you have one side is higher and the other side is lower voices. It sounds better. What I would recommend is that you have to think about your project from the beginning to the end. So the beginning is the plan, and the end is the projection of your documentary or your thing. So making your things only for as a project on your computer is not the end of the work. The end of the work is when you hear the applause after seeing your work. So you have to think about the system on which you will show things, because if you will decide, for example, that you are using something like my booth, it defines how you should work on the material. And if you want extreme resolutions and audio orders, you should do it for specified hardware. So you won't do file that is very rich in data and give to someone, and probably they won't be able to watch it. So if you want to really go for the best resolutions, you need to make it for specific hardware. This is why I made my booth, to have such possibilities. And yes, the sound is important, but the video is the bottleneck of everything. So probably you noticed that there was a big difference between the recording from the Ambio and from the Zilia in means of spatial resolution. So I would probably recommend working in second order. Third order, comparing to the second order, is not such a big difference. If you would do a blind test, probably not many people would recognize the difference. But between the first order and the second, there is a great difference. So if you will manage to do mic or for example system of mics that works in second order, it's better to do it this way than in the first order. Or you can do the reconstruction as I am doing. It also can work, but you have to have the spatial pilot from the Ambisonic mic. Because without it, you won't remember the qualities of the spatial audio in the place. So, do I have some more time or?
Is Patricio here? Yes, you have more time.
Okay. Okay. So we'll use it. Okay. So what I'm trying to achieve now in means of my projection booth and the system, I would like to experiment with projects that you can switch from the points of view during the projection. So for example, I want to listen from one spot to other. The problem is that every authoring tool and projection tool, I need to design it myself. I was in Dublin on AES, and there was a talk from Fraunhofer about MPEG-O container format, and they are thinking about doing such things like Ambisonics, 6DoF for video, but they are planning to do it 2022. So forget about it. Gaze-only interface. Why you should gaze-only interface? Probably gaze-only is not the best recommendation right now because the speech recognition systems are getting better and better. So maybe speech interface is also good, but I not recommend to use hand interface because it gives many clunkiness in your project. If you want to show videos, do it in a way that someone puts the headset on his face and doesn't need to use hands on everything else because he's blindfolded, and even if the for example the touch controller is mapped inside the VR, he needs to grab it and put it away. People are not used to use VR equipment at all. Adaptive bitrate resolutions and orders. That would be nice. For example, for streaming. Imagine you can stream audio through the internet, and you can have adaptive Ambisonics order depending on your bitstream. That would be nice. Personalized edge ATFs, which are the holy grail of the Ambisonics binauralization right now. And I don't know how to get it. Many people said that they know how to do it without special equipment and anechoic chambers, but they were only talking. Maybe someday. GPU rendering of video and audio. That would be nice to have additional computing power for the projects because they are, as I said, really power consuming. Multiple spectators at the same time able to communicate by voice. This is something that Oculus and other producers are thinking about when you have cinematic projections, and there are those virtual cinemas when you can sit with your friends and watch. So imagine if you can be on a concert and in somehow communicate with other person that is watching together with you, and you don't interrupt the performers, but you can talk about the performance. It would be nice feature. Okay, custom menu. Okay, this is something like I would like to have. And I was talking about, because why I'm here? I'm here to talk with engineers. I'm creator, I'm director, I would like to have good tools. And you are the engineers that I'm asking for those tools. And what are the tools of my dreams? My tools of dreams are, for example, ecosystem of tools that are working together and that I'm not made to switch myself to different systems many times. Online monitoring and mixing with VR. This is something that I would like to achieve in next year, because I'm starting to work with Polish movie school in Łódź, and we are now exploring such idea about streaming in VR music concerts from the Chopin concourse. So we need to have monitoring tool. Imagine sitting in a room with headset on and listening to the music through the Ambisonics and in sync. That would be something that we would need to have at the moment of making such streaming. Tool for Swift HRTF profiling. This is what I was talking about, the holy grail. Something that I can employ into my project and to hear things not as KU100 or something like that, but like my head. There is no authoring tool, unified codec container players ecosystem. I need a player that I'm not making my own player that is made by some software developers that can have high resolutions of video and high orders of Ambisonics employed. More efficient compression methods. I have such vision that in 3D video and audio there is much redundancy in data, which can be somehow reduced by efficient compression methods. So if you compare images from left eye and right eye, I believe that the lot of data is the same. So it could be somehow limited, because the bit rates are like 85 megabits is like normal VR video. So I don't know if this is needed. Okay, and native support of up-to-date 3D 360 formats on popular platforms. There is no native support of VR on PC and Mac in means of video formats and audio formats. You have to use special metadata to make players know that this is 360 video. It's not like that at the moment. And we are 3 years since Facebook released first commercial version of Oculus, and now we have the next wave of the headsets. Why the system Mac is not VR at all? I don't know why this is the situation right now. Okay, so basically this is all of my presentation, but I will be glad to show you on the headset the presentation of the recordings. And if you have any questions, I can answer.
Okay, thank you very much. Okay, got time for a few questions.
Yeah.
Alex, yeah.
If you're recording with several different microphones at
Yeah.
the same time in different positions, how do you make sure that positionally they sync up with the video in the end?
Well, this is all based on iterations. So I place the sound and check with the video because there is no other method to do it. You just need to make it by your ear.
I might need help with this question. Because it's been a long time since I've dabbled with any ambisonics. I seem to remember there's extrapolation methods to
Mhm.
go from one order to approximate a higher order.
Yeah.
Is that correct?
Yes.
Yeah?
Yeah.
Yes.
Yeah.
So
Yeah. Yeah.
just making stuff up.
Yeah.
Very well.
Oh no, they're cleverer than that.
Okay, cleverer than that. I'm just wondering whether they've been any use to you, working in first order and then avoiding the potential issue of image blur, extrapolating
Yeah.
to a higher order. I
Yeah.
don't know whether, because that would keep your
Yes, I
records
have
down.
tried, for example, Harpex, and the results weren't as good as recording with the higher order
Right.
microphone.
Yeah, of course.
So
It works in the frequency domain, so it can only track maybe. I've seen the source code, so I have to be a bit careful about what I say. It only track a certain fairly small number of objects, and after that, it probably makes things worse.
So would you then aim to record in the highest order possible and then maybe present in a lower order? Is that
yeah,
right?
yeah,
Okay.
that would be the right way to do it.
Okay, cool.
Yeah, I would love to try recording with EigenMic, but we don't have yet one.
I might be able
So.
to find you one. So, just out of curiosity, when you're talking about the containers and all the rest of it, is it still all mucking about with Python? Is that
Part of it, yes.
part of it? Right.
Yeah.
Okay. So it hasn't moved on from
No,
that.
not really.
Good to know. 'Cause I'm not
Well,
going back.
the best tools now for me that are most interesting, for example, are DearVR, Spatial Connect. This is a tool that you can put your headset on, and you can play video. You're inside the VR video, and you can place the spots with sounds and move them. And you have virtual mixer. You can do some things inside the VR space. So I believe that editing VR should be done in VR. Yeah.
Cool.
So this is the right direction. And Adobe also has something for video editing in this way, but it is a bit clunky. So and the unedited video. The raw videos from the cameras are so big that you have to downgrade them to make them editable, and based on this addition on the smaller files, you can render the bigger files into the final edit.
Any other questions? Okay.
Yes.
Firstly, don't worry about VR dying. It's died before, and we're all still here. And I think AR is going to make a big difference to sustaining the specialist VR
Yeah.
aspects, which are problematic for the nauseous reasons you pointed out. But my question is, why do you think the GPU is going to help you with audio?
Yes, because the higher orders, you have plenty of data if you use them, and if you want to edit them, all the channels at once, for example, make some manipulations, and do it with the video, maybe putting it all in the GPU would give you more power to do it.
again. So thank you very much for that talk. Really interesting.
Thank you very much.
So we've got another break now. We're only like 3 minutes earlier than we should be. So that's worked out quite well, really. So if you make your way back to MS005, perhaps take the time to, there's a headphone demo from Alex Patel. You're doing a talk at 4:15. There'll be a headset to try out. So if you make your way to 005, then a larger example of the gas guitars with Ambisonic Spatial Performance System. Ooh, nice. But before that, we're pleased to welcome back Alex and also, is it Michele? Michele Lucci. They're giving us a talk on the individualization of HRTFs using MEMS speakers to accurately reproduce pinna frequency shaping effects, which you may have listened to a little bit of in the room that we're having coffee and teas. If you haven't, they're here tomorrow as well, so you can listen then. Alex Borcasis is currently an acoustic engineer at USound, who's specialised in the production and application of MEMS speaker technologies. He is responsible for the development of 3D audio headphones. Whilst working full-time, he is also studying for a PhD in spatial audio reproduction methods for theatre here at the University of Derby, where his current focus is analysing driving functions over planar speaker arrays. And Michele Lucci is a hardware developer at USound in Graz, Austria. In 2014, obtained his BCs in electrical and acoustical engineering from the Technical University in Graz, and is currently working on his master degree. Michele has gained professional experience in the field of electronics development during his studies, and since 2007 he is working on the topic of cue preservation headphones at USound, where he has contributed to scientific work in the field of improved localization in the medium plane with cue-preserving headphones and evaluating out-of-head localization of a dry source from the front reproduced with cue-preserving headphones. So, I'm looking forward to their talk. So, thank you very much.
So, thank you for the introduction, Bruce. So, the contents, what are HRTFs? I mean, we probably all know that here anyway. The problem with them, how can we solve the problem with HRTFs? And a bit about our technology and MEMS speakers in general, and then what we call an MPTF, which is a MEMS pinna transfer function, so basically a near-field HRTF, and then kind of how do we use all that to drive some headphones. So just briefly, HRTFs, in the horizontal plane we use interaural level difference and time difference in order to localize a sound to a specific position. In terms of different time of arrival and the level between the ears, which again we probably all know. And then in the elevation plane, we tend to use the frequency effects of the shaping done by the pinna. And we can see here in my, is there a laser thing? No. Okay. Well, you can see there that in my HRTF, for instance, there are notches and peaks as elevation increases as well. So they're individual to each person. And using a general HRTF to reproduce localized virtual sources will give a poor result in most cases. So we need individualization. So the problem with HRTFs is everybody's ears are different, and general ones are just rubbish. So how do we solve the problem? We need to excite the pinna as if they are coming from, to give the same frequency shaping as if they had a real source in that position. So to do this, we can compare free field HRTFs and close-up near-field MPTFs, as we call them. We tried using standard electrodynamic speakers, but because of their size, they cause lots of unwanted reflections in the headphone design, which ruins any of the spatial effects that we're trying to cause and completely ruins the frequency shaping. So we needed very small speakers, and that's where the MEMS speakers come to the rescue. So the basic technology relies on a piezoelectric crystal structure that is excited with electrical current, electrical voltage, and it then acts as a cantilever that drives a bigger membrane. We've got a standalone version of our MEMS speaker in the coffee and tea room if you want to have a look at it. But it's very, very small indeed, contains many layers, and yeah, it took quite a bit of work to get a product, I think. So what are the frequency response of our MEMS speakers? We can see here that up to, it's quite low resolution. We have about 73 dB at 3 or 4 kilohertz and above, and this is driven at 15 volts DC offset and 15 volt peak inside a little housing. So we have a little box with a back volume to get rid of the acoustic short circuit. And then on the right hand side we can see a biquad filter generated to linearize the response of the speakers above, I think, 2K or 3K. This is 50 samples on the left, and we can see the frequency response is quite similar for all of them. So we are getting there with manufacturing techniques to deliver reliable products within a plus minus 1 dB range. So we do MPTF measurements. So these are the MEMS pinner transfer functions. And we started off doing a very simple method where we had a 3D printed skeleton structure, a single loudspeaker, and we would move that around the ear on a KU100 and record the impulse responses. So we could then compare that to a KU100 HRTF and look at the difference. We then, from that initial data, we then chose 4 positions and went on to build the prototype headphone, which is in the other room. We then analysed or used that headphone to capture more pinner-related transfer functions on actual people as well, rather than just on a dummy head, along with HRTFs of the people as well. The Acoustic Research Institute in Vienna, who've been very good at helping us. Now the next step is what we call the jellyfish, which has 16 MEMS along its arc, and that can be rotated, allowing us to get 500 impulse responses, categorizing the frequency shaping around the whole ear. So here we have my HRTF on the right and the MEMS pinner transfer function on the left, based on the middle headphone design there, which is quite sparsely measured actually, because rotating a full bulky headphone is quite difficult to map all the positions and get them consistent. So we can see there are frequency shaping effects that are similar. Notice though that the scales are different, but we have the notches and peaks increasing with the elevation angle, similar in my HRTF on the right. There are some issues with these measurements because, as I say, the resolution in some areas is not very good. That's where the jellyfish on the right will come in. So we can look at the magnitude spectra of the MPTFs and see that as we track one speaker around at different positions, the impulse response, the frequency response changes, which is what we want. So we've shown that we can excite the pinner to induce different frequency shaping. The woofer also does not show much effect on the frequency shaping, which is good because we only want to use the woofer for driving sub 2 kilohertz, where the MEMS roll off too much. So we indicate that the headphone can create spectral features, but a weighted sum, so treating them more as an array, would likely give better results than just having a speaker playing sound from that source, equating to that virtual source angle. So Piotr at the Institute has got a very nice sound localization model where you can select the ability from a pool of listeners, the localization ability. And here are 2 examples with an average localizer and an excellent localizer on the right. So on the left image, we have if I was listening, or if someone was listening to my HRTF as a average localizer, we see that we have a nice clean, well, a clean-ish band going up, which shows us the reproduced angle and the target angle. So the model is assuming sounds played from all different positions, randomly pooled each time, and the probability of that listener with that baseline prediction value of S, saying that yes, it's coming from that place. And on the right-hand side, we see it with an excellent listener on this image here. Now, what is not good is the fact that the other two images look nothing like those. So this is the probability of somebody listening to the headphone in its current state and saying, okay, the virtual source position matches where we are panning it to, if it's just a direct source playing. So how do we make that better? Well, we need a driving function in order to drive the MEMS and get better localization. So we have an unknown. So we have the individual HRTF. We have a MEMS spinner transfer function and an unknown driving function. And what we need to find out is this driving function, which will translate and give us the difference between the MEMS spinner transfer function and the HRTF. So it's about adding the signal processing to the MEMS in order to reproduce the HRTF as if it was played on a free-field loudspeaker. And we can do this for multiple listeners as well. But first off, we need to look at the equation a bit more closely, introducing some errors. So we have the sparsity of filters, because we don't want to have a huge filter bank as well. We want it to be relatively efficient to run, and also the number of speakers. I'm sure with 1,000 speakers you could get a perfect reproduction, but again, it's about practicality versus what is theoretically the best solution. And that's for average for multiple listeners. And that's what we want to end up with, so that anybody can put on their headphones and there's a generalized filter that creates the frequency shaping required in the eardrum as if it was the individual's HRTF. So this is what happens as you gradually reduce the number of speakers if you were to look at the array as a whole based on the headphone measurements. And we can see that once we get to 16 speakers, the error in localization greatly increases. So it seems that between 16 and 12 individual channels treated as an array will give us the best localization in terms of angle error for the listener. And again, showing the localization error as a number of speakers. So we're currently at 4 speakers. So the quadrant error and the polar error in degrees is rather high. As we can see, as we get to about 12, it is much reduced there. So the next measurement steps are to use this jellyfish to get lots of people, get lots of data of HRTFs and MPTFs that we can plug into the equation earlier. It's important to measure an equal number of men and women in order to get various ear shapes, sizes, and HRTFs as well. In a male-dominated field, it's good that if the product works for everybody as well. So we need to solve the function for one user and then for multiple users to get that generalized driving function, and then increase the number of MEMS in the headphone to roughly 12 or above to give the correct frequency shaping response. And then hand over to Michaela. Talk about the hardware and electronics.
Yeah, hello, thanks for having me. Good afternoon. Yeah, we'll be talking a bit more about the hardware and all the things that you can touch and see and listen to in the other room. You see here a picture of the headphone already, pretty much 3D printed cups and custom electronics. So you can have a USB connection to the computer there. Basically it will pop up as a 16-channel sound card, of which we are using only 10 at this stage, but you could upgrade if you wanted to have more speakers. Obviously a power supply, because USB power is just not quite enough in this here right now. and 4 MEMS speakers per side, and as Alex mentioned, a woofer for the low frequency part, as the MEMS are just, they don't have the surface area simply. Right. So you see already in this picture, it's quite open. So it's not just an open design, it's like super open, because we found out that pretty much any obstacle will just ruin the frequency response. You can see here this response. I mean, it's a bit, if you're looking just at the response, you can say, oh, well, there is a notch, that frequency matches more or less. So you can say, okay, good, fair enough. But it's tricky to say that this is going to have the same influence for everyone, right? So, yeah, for some person, maybe introducing the woofer, as it's shown on the left picture here, wouldn't even make such a difference, but for someone else it would. So really make it as open as we possibly can. So there we go. The woofer is really displaced to the side completely. The arch where the MEMS are placed is let's say as small as it can possibly get. And then it's also a matter of foam pad material. The memory foam, for instance, it's really not that good because it's still kind of closed port. I mean, they are semi-open because it comes back to the shape, but if you use it, you can see already some waves, basically, the yellow line. Oh, sorry, you really can't see that. So red was the reference without any foam or obstacle. Then you would have gray would be, well, the gray foam that you see that we are using at the moment, and yellow is a memory foam. So you see that there is an influence. We tried different foam materials, and really we have to go as transparent as possible. And the woofer, yeah, it's displaced to the lower end. As Alex said, you can move it all the way around the circle as you prefer. It's not really that relevant below 2K. And so we've moved it to the bottom. Yes, I mean, we are a company, and we're always pushed by our bosses. Well, we want the product, we want to sell this and so on. So we are doubting that we're going to be able to keep it there. So possibly, honestly, it will have to move over the year, and it's going to have to be a trade-off there. Right. So, oh yeah, everyone, pretty much everyone has been asking, what's the PCBs up there? That's the custom electronics. Here's a block diagram. We are using an STM H7, very, let's say, variable platform. It's not perfectly suited for DSP applications, but you can do a bit of filtering, and mostly you can have lots of interfaces, so I2C and SPI lines. Pretty much it's the center of the system right there. It emulates the sound card, the 16-channel. At the moment, the signal processing, so let's say the filtering and most of the processing is done, well, all of it basically is done on the computer. The H7 is just not cutting at this moment. Also, power consumption is a problem, so we said let's keep it on the computer because there's the power is available. And then there is a connection to the right-hand PCB, which we are using a serializer for. So everything is time division multiplexed. So you have TDM8, which is, well, it's quite similar to AES audio format, just lower levels, let's say, a few different things. So 8 channels left, 8 channels right. We are discarding 3 of them on each side. But then we have on the left an IMU. So as Alex mentioned to some of you, there is hardware for motion tracking that we are not using at the moment yet, and there is a pair of microphones for beamforming, for very important for gamers, I guess. So these are the MEMS. You can see them over there. This is the dimensions, so 5 by 3 millimeters roughly. And this piezo material, you drive it basically with higher voltages compared to, let's say, a dynamic driver. But you should never, well, in our case, you can't go, let's say, negative voltage, right? Because the distortions will be quite bad. So we put a DC offset there, and 30 volt peak is basically the driving voltage that we are getting at. So, then one of the big questions, or the big questions, is it good? Yeah, and as you may you understand that it's very difficult to say if it's good. I mean, the questions we get is, well, how loud is it? Yeah, you can play all the MEMS at the same time and also the woofer and just give it all it's got. But in a reproduction scenario, that's not very likely to happen. Yeah, because you're playing front source, back source. Okay, of course, if there is sources all over playing era, you might get there. So yeah, how can you measure the loudness? So we're doing it in steps. So each single speaker, then all the MEMS speakers at the same time. So we're using frequency sweeps. Then only the woofers and all the drivers. Then of course, how does it sound? Okay, yet again, you can use frequency responses to do that. But if you record the frequency response of one single MEMS speaker, I mean, you're gonna get, obviously notches and peaks and so on. And that's gonna be useless, because somebody is gonna look at it and say, well, this is not linear, this is gonna sound crap, or not even close to linear. But hey, you've measured it on a, that's the point of the device, that it's not linear, because it's supposed to include your pinna. So, difficult to say if it sounds good. So, the way we are trying to do it is to, well, there is different ways, but one is to use a diffuse field reference measurement and then balance the MEMS out and the woofer so that they have the same frequency response, maybe on an artificial, so KEU100 without ears. That's one option. The other option would be white noise or pink noise and balance it out by listening also, maybe also to music. So really tricky. But of course, you can come by, have a listen and tell us, well, no, this doesn't sound nice. Okay. And of course, listening tests are always the best way, or let's say not always the best, but they are, I think, the most sincere in this case, but of course, expensive and so on. Does it work? So do you actually hear a difference in positioning? Is it good, the spatialization? Do things come from behind or not? Again, very tricky to measure. I would say close to impossible, because you need to listen to it and each person must tell, okay, yeah, that works for me, that doesn't. So in that case, I would say, please come by, listen and tell us, because that really helps us. And don't be nice if you don't, well, be nice if you like to, but be honest and say, okay, that works for me or that doesn't work for me, because that helps us a lot. Okay, any questions to Alex or myself?
Thank you very much.
Thanks. Ooh, don't step on it.
Mic drop.
Yeah,
Have you got any questions? Steve?
I'm just wondering, with the question of actually mounting the woofer
Uh-huh.
and causing, I guess, just a really strong first order reflection, right? Is that the main issue?
Mm-hmm.
Is there any way that you could actually just counteract that with a filter, or do you just run into the next problem and so on? So you just keep.
That's exactly what happens here. That's one of my colleagues said, yeah, well, if those, he looked at this graph here. He said, well, if you don't want that notch, why don't you just put a filter to delete it?
Sure.
Exactly.
Right.
So you end up with you just end up.
So yeah, sorry, these are actually quite severe, right? And they're
Mhm.
a direct result of putting them.
Yeah.
The woofer, right? Okay.
Yeah.
Yeah.
So, yeah.
Yeah, forget that.
No, that's a fair question. So in the ear cup, it's like you have to just make sure you don't have parallel surfaces, you don't have flat areas. You need to convex, concave, and all these kind of things to get rid of reflections.
Any other questions about the MEMS microphone?
Just wonder, is there a reciprocal MEMS mic that you could use to measure your MEMS loudspeakers? Is it nice and small?
So it,
You go ahead.
well, we don't have a mic, but you can use that speaker as a microphone.
I'm just wondering whether that would be useful for actually picking out, because you could actually build an array of measurement
Microphone?
games, and then
question. No,
It's like
we haven't.
getting the sound fields recorded in that. It's just a problem of space, right?
Yeah.
You can't stick an amp, B format mic in there and try and pick up the resolution. But if you had a little tetrahedral MEMS mic, you've got an A format.
Yeah.
So.
Get Charlie on it.
So in terms of your, so at the moment you're driving it with a 5.1
Yes.
stream.
Yeah.
So ideally, what would you want? What audio format would you like to drive your system with? Because it's not, you couldn't really use binaural.
No.
You couldn't really use, I mean, you can use 5.1, 7.1, but you're missing out the height stuff.
Mm-hmm.
So what is it from in an ideal world would you want?
Ideally, I think we talked about 7.1.4.4.
Okay.
Yeah.
So you're still thinking discrete?
Yes.
Discrete.
Yeah.
6 in the middle.
Yeah. Yeah, I mean, that's staying on a convolution-based system. If we do move into more of a driving function with head tracking, etc., a bit more dynamic, then an object-based system would be probably useful.
So then all the object processing would have to happen on the headphones. So that would be quite meaty. I'm just wondering whether you've investigated the spoke harmonic ambisonic route versus the discrete channels. What would be best? What's the limitations? It sounds like a really interesting problem actually working out. And you might end up just going, well, actually, all we need is sum up, sum left, right, sum up, and then we can, the rest is blending together anyway. We could try image elevation, just squirting a bit of mid frequencies to lift things up. Yeah. Which I guess then when you've got the object based, you could then go, okay, I've got this object base. Actually, what are the shortcuts to getting?
Yeah, because we were speaking to Simon earlier, and one of the things that we've discovered is really hard to get any content with elevation. Yeah, we've been in touch with quite a few people, been promised to have been sent things, and yeah, it's just really difficult to get any content with elevation that's not Dolby Atmos. We haven't got an Atmos receiver or anything to do that.
I mean, that's where, at the very least, Ambisonics might help.
Yeah.
Because there's plenty of content on YouTube that you can download. So there's quite a lot now available, isn't there?
Yeah.
So from getting something height-wise, perhaps Ambisonics might be useful just for that, even if it doesn't end up being actually the ideal format. You'd have some extra, because often with these things, it's great having little, your test graphs and stuff, but sometimes, like you've got in there, you want like a game, you want something a bit more dynamic and interesting to actually get a feel for how it works.
Yeah.
So.
Because at the moment we've got the L2 and the L3. They're not even used at the moment. We're just using the front back MEMS. Yeah.
Which is interesting, and like I say, it was a good argument to go and buy a gaming laptop and get games.
Yeah.
Which is always nice.
Have you done any of your measurements of people's ability to sense directionality with head tracking?
So that model is from the model that I showed with the black and white graphs. That is from the Acoustic Research Institute, and I'm not sure of their protocol to do that.
Okay, I think it would work.
Oh yeah, definitely.
But the other thing is, if you want to use a game as a way of detecting whether or not people's localization is better, just make sure that there's something chasing them they can't see and find out how often it gets them.
The Darwin approach. You survived the longest.
That's a good idea.
I like that game playing. Are there any more comments or questions? This is probably the most stupid thing I've come up with today, but just going back to Adam's talk from earlier, and the idea of actually firing low frequencies straight into your brain. Is that something that you're at all looking at, this idea of bone conduction?
The bone conduction, I have mentioned it once or twice, but it didn't really, didn't really take off as an idea.
I wonder if anyone knows what kind of roll-off you got for that kind It's not great for LS. It's a bit like this system, it's great for your higher.
Really?
For LF, you start touching stuff.
Goes with that CK rate, isn't it?
Oh yeah.
Because that's
it's lower
running off at 4 really.
But yeah, for your sort of your actual real bass, it's not.
Although we've been getting some products in to listen to, and they had a Razer gaming headphones which have actuators in that vibrate in order to give some kind of LF effect, and it's just like it's like just someone's farted all over your LF. It's not it's not great.
And you get a headache.
Yeah,
after
you
10
do.
minutes,
You can
like-
actually feel your eyes vibrate if you turn it up to 90. It's yeah, yeah.
Not heard that. I've not heard that. That's that Razer headphone.
Yeah, Razer. Yeah.
Okay. Any more? Okay. Well, thank you very much. It's a really good talk.
Thank you.
So next up is Emma and Duncan. Duncan.
Sorry. Annoyed about things not being loud enough.
Oh, he wants it louder.
Yes.
He wants
Just tell me to turn it up.
yeah. Well, start getting your mic on. Just talk amongst yourselves for 2 minutes while we wait for Duncan's doing a demo upstairs with Emma, so I think they're just making sure that's everything as good as it can be.
Yeah, no, I'll turn on a minute.
Sorry about that. So,
Yeah, thanks. Shall I start?
That's all right. So next up is Duncan Werner and Emma Fitzmaurice talking about the gas guitar's ambisonic spatial performance. Both originate here from Derby, at least educationally. Duncan works here as a senior lecturer and started up our music technology degrees many years ago. And Emma Fitzmaurice is one of our master students who also came to our undergraduate courses. And both have been working on the gas project for a couple of years now, I think.
Yes, indeed, at least.
So there'll be a talk now for half an hour-ish, and then we'll move upstairs where there's some live demonstrations and some other bits and bobs.
Optional.
Yeah. Oh, I need to sit here, don't I, to do your audio?
You do, please. Great, great. Do I?
So, slides back and forth.
Okay, we'll see how this works then. Excuse me for being out of breath. We've just come from trying to set something up upstairs and make it happen. Gasp, guitars with ambisonic spatial performance. Fred, come in. Yeah, yeah. I'm Duncan. Emma, that's a guitar. We've been working on this, as Bruce says, for a while. Is it this one?
Left and right.
Left and right, okay. So what is GASP? It's a project we've been working on which has got two angles to it. The idea being, one, a technical kind of adventure, exploring ideas, utilising technology, using it in alternative ways than perhaps it was intended. So in that sense, we can say it's an innovative audio project, fusing the musical with the technical. And the kind of key feature behind that is the fact that we're using individual string access. So normally on a guitar you have a single output, a mono output, which you would perhaps process spatially, or some kind of pseudo-spatial properties in some kind of either guitar rig or some sort of virtual processing system. So we've got individual string timbralization. So we've employed some initially bespoke pickups, but now commercially available pickups to do that. And we're combining that with ambisonic surround sound. Largely, in fact, yes, the ambisonic surround sound is we're using Bruce's plugins, which we will see shortly. It's also an artistic musical project. So we want to involve musicians, guitarists, to say, hey, yeah, that really works, or that doesn't work, or how might it best work? So we're seeking to get feedback from musicians and see how well the system works for them, if it works at all, and what might be the future opportunities for us in terms of live performance within either a solo capacity or an ensemble capacity. So production ideas for the guitarist and music producer. Of course, as we're working in ambisonics, then we can easily translate that to binaural sound, which we can listen to over headphones. Previous work that we've done, this was up until more recently when we embarked on how can we make this a live performance instrument. Prior to that point, we were using the guitar for individual string recordings and then doing post-production on that. So the picture there is actually of waveforms of the individual strings that were captured, and then we would use that for post-production purposes, in which the same way that you might take a multi-track recording and you've got you've got the different instruments on different tracks. Well, we've got different strings on different tracks, where we can then process those either individually or as groups. So it's a case of analysing the performance and seeing which strings are working together, which strings have got some kind of time delay between them, what timbres work best. So all sorts of kind of musical parameters through musical analysis of the waveforms to see where the envelopes start and finish, and then make judgments as to how we might process that timbrally and spatially. So experimental production techniques and the ideas behind this, one of the things about Derby University is that we are expected, and quite rightly so, to embed
our research into teaching. So we've offered this project open to undergraduate and postgraduate teaching, and I think in a little while we'll hear one of our postgraduate MA students' tracks. So over to Emma.
Okay. What are we going to play?
Let's play something. Let's play Pale Aura. This is a track that Dominic, say hello Dominic. Dominic was a student with us a couple of years ago, and we got funding through something called the Undergraduate Research Scheme, URSS, Undergraduate Research Scholarship Scheme, which meant that I could work with Dominic and Jack, but Jack isn't here, on some tracks. And this was something that Dominic was interested in. Go. Just to say, that is one performance. There are no overdubbed guitars on that. So all of the ideas that come where we split the signal, we've got different timbres, have all been created from one guitar performance. So there's no overdubs in that piece of music. Emma.
Okay, so this is a live system, which is where I came on board. Walk through the little diagram, which is going to be appearing throughout. So basically, black arrow indicates the audio flow, white arrows indicate the control messages, which are all through MIDI. This has all been done as kind of a building bits of stuff together with only Bruce's panels have been kind of bespokely made for it. So it's not the most elegant way to do these things, but it's the way that has built up part of the future work is to condense this into a better system, really. Starts with guitars.
Okay. So the two guitars that you can see there, they were our first guitar systems that we had, and they're using passive pickups. We managed to get hold of those from the States. We couldn't find anybody in the UK that would do individual split pickups. So a guy called Paul Rubenstein, who makes his own musical instruments, provided us with those. So they are what we refer to as hexaphonic pickups. And the idea is that from the output of the guitar, we've got 6 individual outputs, one for each string, plus the main output as well, if we want to use it as a standard mono guitar. Let you do that. Then further to that, we managed to get hold of a new style pickup, which was an active pickup from a company called Psych-Fi, and they are making that in a much more commercial and robust way on a production line. Again, it was only available from the States, but we got their system. It's not cheap. The pickup itself and the breakout box and everything with import duties cost us about about £600, I think, for the pickup system. Yeah. Okay.
So to get out from the guitar, we need a multi-channel interface. This is the one we're using. It's a bit out of date now, but the important thing is there's not many interfaces that have 8 instrument inputs. So we kind of needed something where you could go jack in and still have a gain control, which is not all of them, but this one does. Basically just it's needed, and that's what it's doing. Then into the software. So all the software I'm talking about, well, the next 3 things are per string. So there's 6 instances of these running in parallel, each being fed by the feed from one string. To get the tone of the guitar, we're using a piece of software called Helix by Line 6. If you're familiar with Guitar Rig or anything like that, this is kind of the latest and greatest, fanciest version that will run in a plugin. So it's got amp simulators, stomp boxes, all sorts of stuff. So this is an example of a patch in one of them. Starts in the top left. That's a volume, splits off, goes to a couple of delays, a couple of amps. So each of those blocks is a processor, and that builds up your patch. And it's mono input, stereo output. So this is kind of our first step of making things bigger, which is to come out stereo. This is the gate. We'll get to the gate in a minute. It's there. It's part of a concept called the guitar arpeggiator, which is always good because it's a pun. And yeah, it'll make more sense once we talk about the Ableton system, how it integrates. Spatializer is this chappy. This is made by Breeze. It's a 3rd order, but only 2-dimensional, because when we usually work in is 8-channel 2-dimensional array. Again, 3D's in the pipeline, something to do future, but there's quite a bit to this with stereo input. Again, Helix stereo output, stereo input here, 3rd order. So, yeah.
Okay, just flick back one. So the idea of the spatializer is that we've got the blue and the red. That's the left and right channels of the output of the Helix processor. So we're operating with a kind of a pseudo stereo signal. The white blob is the center of the image at that point. So if we were to listen to that, we'd hear all the left side coming from, all the right side coming from the right, the left side coming from the left. And we've developed tools, Emma's been quite proactive in developing some of the tools that now allow us to manipulate that in real time for live performance. So there are 3 kind of parameters that we can discuss, and this actually came from, I believe, I know they're your pickups, Bruce, but it was Joe Callister, who was a URSS student that sort of, manipulated the software such that we could use it in this fashion. So on the very left, the spread is the left and right image of one string. So, and you can see the spread is overlapping. So we've got the movement of the left and right pseudo image crossing over and coming back. So you get that sense of envelopment. And then the idea, of course, is when that's multiplied 6 times, 1 on each string, with control for those parameters on each string, then there's a lot of potential processing. The angle in the middle there is where we want to place it. So that's, at the moment, the stereo spread on there is minimal. So we can think of that as a mono signal almost. And that's just rotating around. Of course, we've got speed control, which will allow us to send that signal faster or slower, or change its direction. And then finally, on the distance parameter, it can be a little misleading, the name, but the idea is if you can see where the red and the blue round the edges evolve and then retract around the edge, it's really a case of those sounds being spread around the ambisonic image and then condensed. So it's kind of a localization control as well. And then what we did was then, once we'd figured out how we were going to do these spatializers, we then thought, well, it would be a good idea to make a bank of presets in much the same way that you would have a bank of presets on a any guitar foot pedal system.
If you come up later, they won't be this jumpy.
All right, they are moving. Yeah, okay. This was the GIF that was. So you can see on the left we got 6 there. So the top 2, and we've not got a pointy thing, have we? No. Okay. So we've got the top 2 are the A and the E string, and then we've got the D and the G, and then the B and the E. So and what's happening in that particular configuration, we've got a star system. So you can see that the first 2, they're moving just left and right, and then the 3rd and 4th string across one corner, and 5 and 6 are across another corner. This, in reality, would be moving smoothly, which we can show you in a little while. And so we've got about 20 of these different presets, different spatial presets that we've created. And then on the right, that's another one where, gosh, that is a slow Mac. So what should be
happening? It's just spinning around.
Yeah.
The width's staying the same, and each string is offset, spinning in a circle.
Yeah. So the top left string there is rotating clockwise. The next one to it is anti-clock. The next one is clock, anti-clock, clock. So we're sort of trying to experiment with different variations to create a sense of immersion in the performance. Great.
So also, you see sound effects. There's not a great deal out there in terms of ambisonic effects processors, but here are 2 that you've messed around with. Top one's spatial delay. So that's it's a 3rd order delay with rotation in the feedback path. So the bottom 3 controls of the top picture are your pitch and roll. So essentially you can say every time it feeds back into the input, it's rotated by 60 degrees or whatever. And then as you get the feedback, you get more repeats that keep jumping around the circle. The second one is another of Bruce's things. It's called the Ambi reverb. It's just a 1st order reverb thing, but it's reverb. You don't need high order reverb. Yeah, so they're just sent again from each string independently. If you want really reverberant high E and everything else dry, we can do that, and vice versa, whatever. In terms of the control system, it's based around Ableton, which is running on a separate computer because the internal MIDI routing was being a bit strange in terms of patch changes for Helix. But essentially, you've got the 3 elements: the spatializer, the temporalizer, and the guitar arpeggiator, which is still coming soon. Spatializer, again, it's like those things, the GIFs that didn't play particularly well a minute ago. They're all the different variations of those that kind of have been set in, and it's just patterns of CC control written into clips in Ableton, and they loop, so they'll go for however long you want. The temporalizers, they're just patch change messages going to, the patch changes go to every string simultaneously. They all have to remain on the same patch. However, Helix has a thing called snapshots, where within a patch you can have variations. So that way we can get different timbres on each string, but that's very much work in progress and doesn't particularly work right now. Yeah, so this is, again, it would be better if it was running smoothly. This is related to the distance parameter in the first spatializer. It's got this kind of triangle wave shape because as it loops around, it's going to go from kind of middling distance to all the way out to all the way in, and then it'll loop round. And yeah, so this does show some more things. So if you want to get it to go in a circle, you need a sawtooth wave, and which direction you do that will determine which direction it goes round. It has shown up. So yeah, so again, so this will be the highest point and the lowest point are both right at the bottom of the circle for the ankle. So it kind of overlaps there. So you need to have a sawtooth to make it in a circle.
Stuck.
You're animated
GIF has
Oh, we're gifting
absolutely
out.
killed the computer. Hang on.
You mean the non-animated GIF?
Yeah, you've actually crashed PowerPoint. Hang on. I don't remember what the shortcut is.
Well,
but
It wouldn't be music technology if we didn't crash something.
what slide were you on?
Just go.
This one, Bellward.
Yeah. Okay.
About John. So yeah, so to have performer control of this, because what we do a lot of the time is someone saying Ableton, pressing things, but it's nice to have the guitar player be able to use it. And this is just a programmable MIDI pedalboard that's sending out MIDI notes whenever you hit a put switch, and those can be assigned to trigger the appropriate clip for whatever you want Ableton to tell Reaper to do. So it's a bit of a chain, but it works. The other thing is Duncan was mentioning adjusting the speed of how these things are happening. Because they're clips in Ableton, they're linked to bar length. So they're all about a bar long. Some of them are slightly different if they're odd time signature type stuff. But the rightmost expression pedal is controlling the master tempo of Ableton. So that's how we get to kind of variably control how fast these movements are happening. Also links to the guitar arpeggiator, which I've built out a lot now. But yeah, it's slightly janky because it goes on a linear mapping from 20 BPM being the lowest to 999 BPM being the highest. But it's kind of, there's a point where it's kind of becomes kind of indistinguishably fast. When you get it going incredibly fast, you get interesting modulation effects as it's going too fast for kind of the speakers to really have much of a window to represent. But
we can demonstrate that.
Yeah, we'll demonstrate that. But you don't get a lot of control in the kind of slower regions where it's more able to sync to what you're playing in terms of motion. Okay.
Right. So the interestingly named guitar arpeggiator is something that's based upon. Okay, so we've got a set of gates. So we've got on each string we've got some audio gating, and those audio gates can be controlled from the output of MIDI note on messages, MIDI note on and note off messages, as 6 discrete values for MIDI note messages. So effectively we can create a rhythm on each string by switching the note on and off. So you pluck a string normally and it attacks and then decays. So bang. If you do the same with the switching in, then effectively you're switching that note on and off. So you go bam, 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 bam. Or you could arrange that to be at any kind of interesting rhythmic possibility. And then so you've got that on each string. So the combinations of each string with the rhythmic possibilities of the gate switching on each string can give us some interesting possibilities. We hope to demonstrate that later. And that's a GIF that seems to be running quite well. That's switching. You can see then the MIDI note on and off. That's a snapshot from a GIF from Ableton, and then the audio is being triggered by that. So each of those note numbers on the up down axis are individual strings, and that the blobs there are MIDI note on offs switching.
There's been a couple of offshoots of kind of thoughts we've had while doing this. This was an alternative way of looking at separating the guitar. So instead of doing it by string, do it by frequency content. So it's basically a 6-way crossover, slightly bodged together with what was installed in Reaper to do 5-way then 3-way. But then we're sending each frequency bin that's output from the crossover down the path we use to process a string. So the same amount of control over helix and spatialization and even the guitar arpeggiator can be applied to specific frequency bands, and they can all be localized differently. It's kind of, it's less dramatic in effect, but it is still kind of bigger than anything you can achieve with a kind of standard style guitar rig.
And timbral morphing, we wanted to experiment with not just the spatializations, but also what can we do timbrally. And so the idea is that we can take patches, guitar patches, and effectively morph or blend from one patch to another seamlessly. We tried to do this initially with parameter change controllers, but Helix only lets us support, I think, up to 16 variable controller messages, and the patches that we were using have got many more variables than 16. So we then decided to do it as an audio blend rather than a control change blend. And Emma repurposed the, now this is actually a panner, a directional panner, but we've repurposed it for timbre. So that was actually a quad panner, but each quadrant, instead of now representing a place in space, is now associated with a particular timbre for the system. So if we just click the next one, then that's an example of how that displays itself. So as we move, as the puck in the center there is moving round the quadrant, then each, so for instance, this helix would be in place now, then as the puck moves up, it moves up to that. So it's effectively morphing between those different timbres. And of course, each timbre has also got its own spatializer. So we are sort of seeking to morph both timbre, although actually no, we're not morphing the spatializers, are we?
The
Need to think about that.
spatializer is associated with the timbre as opposed to
So I guess
script.
yeah. Okay, so that was an example of what we were seeking to do with timbral morphing, and we have an example of how we have realised that with Cat Fantastic. Now this was a piece again played by one of our URSS students, and we've recently just got round to sort of to timbralising it and spatialising it. So it's work in progress, it's a bit of experimental, but you'll hear, I hope you'll hear the variations in timbre and as well as the spatializations. So moving on. So we're coming to the end of the talk. Future work, there's lots on our list, more things than we have written down there. However, we are exploring funding for a PhD studentship to be able to sort of realise the system in a sort of a reduced way, perhaps building it into a plugin. To maybe look at some possible commercial gain, I don't know. So rationalization of the system, we're looking at something that uses bespoke timbral processing. So instead of using Helix, which is a very processor-intensive piece of software, if we can develop our own processing software that's a bit less intensive, we'd realize that it won't maybe not have the same degree of facility, but if we can do something like that, then it means that we can start considering this for multiple instruments as opposed to a single guitar. Because at the moment, the processing power on our Mac Pro is at its limits. So with a single guitar, with 6 helixes running, with 6 spatializers running, we're at the limit of the system processing. So we need to find ways that we can be more efficient with the processing. We are operating currently as a 2D only, so you know, clearly 3D is an option. We need to be thinking about what, you know, possibilities there are for spatial processing of the guitar in a 3D environment. And of course the possibilities then of translating that into a binaural playback system for use on headphones, because of course not everybody's got a full ambisonic surround system at home or, you know, at work, unfortunately. We've been funded by all sorts of people. In fact, only one person, Derby University. These are the areas that we've been funded through, all very legitimate and, what can I say, appropriate actions taken when we needed some money, and thanks to all of those people if they are here or know anybody that's associated with that. Previous contributors: Bruce, Charlie Midlicott, Sam Speakman, Tom Lawson, Tom Waitman, Joe Callister, who did the panners, Dominic Delali, who's in the audience, Jack Hooley played that piece that we just heard with the guitar there. Charlie Box is in America. Beth, I saw her earlier, she might be in the room. No, don't know. Tom, I think Tom's in the room. Yep. Emma, Harry's here, great. So thank you to everybody that's made a contribution. It would only have been possible with all of these people. Stuff about where information can be found if anybody wants to click that. If you've got any thoughts, ideas about where this might go, if you've got an interest in it yourself, if you're a guitarist or into surround production, we'd be more than happy to hear from you and discuss stuff. So there you have it. I think we are...
Any questions?
We are done. We are done. Thank you.
Okay, so the next slot in a few minutes will be upstairs. So I don't know if anyone's got any burning questions that they'd like to ask at this precise moment. You're most welcome.
Yes.
It's really cool that you've got the tempo control. I'm sure that's a very important extra thing to learn while trying to play the guitar. But I wonder whether or not you've experimented with using tempo tracking plugins so that you can derive the timing information without having to manually put it in.
No, that was a thought that got sidetracked by a lot of other thoughts. Yeah, it's something that can be.
Yeah. The foot controller will allow, if you like, real-time, almost a spatial expression control. But
you can also do it by tap tempo, as well as expression control.
Yeah. I think the point that Emma made earlier was that what we found is there's this point in the control of the tempo where it's kind of slow and you can track it to a point where it just starts to go very fast, and it's to do with the non-linearities of the system versus our perception of the way that, you know, we hear those changes. So we're actually Steve Thackeray, I think, who's gone, who's an MSc student, was looking to provide us with some kind of interface that would convert that data such that we would get a much more smooth representation. Yeah, exactly. Yeah.
Any other
Yes, sir.
I was wondering
1.6 Variax?
Yeah, it's quite different. We did, because the Variax has processing on board, and it's kind of guitar modeling stuff, but it's overall, and it works on piezo pickups. And piezo pickups is something I'd like to explore for this, but it still all gets summed together to do processing stuff together.
In terms of the hardware, is it?
No, it's different hardware. Again, because we're using magnetic pickups. I find one of the slides has a picture of guitar. Yeah, I know. Yeah. So they're magnetic pickups. They're Strats with single coil pickups, whereas Variaxes use piezo saddles.
We have a Variax, and we did attempt to sort of dig our way inside it and have a look, but it's complex circuitry, and we thought, well, I wonder if we can access the individual outputs, but it's much more complex than we thought. Good question.
There's potential to introduce some of the features, like we could do pitch shifting per string, like you can do in a Variax, but we haven't done that yet.
I don't know where the 1.6 based in the UK.
I think they're in the States. Yeah. It's something we've thought about. So yeah, no, it's yeah.
One quick question.
Yeah.
Is the project inspired at all by Def Leppard's Hysteria and how you recorded that? Because the guitar tone on that is quite legendary, and they track every guitar one string.
Oh, did they? Right. Yes. No, I did know that.
There's something like 32 channels of
Yeah.
guitar.
Yeah. Interestingly, it's a very different timbre on the individual strings than a combined output. No, the truth is, it wasn't inspired by that. It was a case of the university saying, you've got to do some research. So it was a case of saying, oh well, we'll get a guitar and we'll do things with it. That's where it came from.
Okay, I think now's probably a good time then to retire upstairs. So
yes. So if you are into guitars, you're very welcome to come upstairs. You're very welcome to come upstairs if you're not into guitars. But if guitars aren't your thing, some of it's loud because some of the timbres that we're setting are amp simulators, and they've got a fair degree of harmonic content. We'll try to moderate the level to your likings. We have 3 guitars: the acoustic, the Strat that's got the passive pickups, and the Strat that's got the active pickups. We've got Fred. Fred, put your hand up and say hello. Fred has agreed kindly to come along and play some guitar for us, which I'm really looking forward to hearing. Emiliano has come up from London to assist with a bit of playing. We've got 1 or 2 others that are interested in inputting some guitar playing. So it's a bit chaotic, but hey, it's a guitar. Right, thank you. So we can go upstairs.